live. And we have similar specimens of ichthyosaurs. There is an ichthyosaur actually that died giving birth. I don't know where it is. I'm pretty sure it's at a
Well,
UK museum.
there's loads.
Yeah.
I've seen 3 or 4 just in the UK.
Yeah.
Though my understanding is the question with at least some of them. So yeah, you have got the adult, and you've got often embryos or babies inside, and then there's usually one stuck half out. And I think the original description, and I've certainly seen a David Attenborough program where he says it died during giving birth, but I'm pretty sure someone has suggested subsequently that could be the case, but it could also just be post-mortem swelling. So when things die, they tend to bloat up. That creates lots of pressure, and therefore if there's an exit, something that's stuck inside will get pushed out. Mm-hmm. So it could well be that a bunch of them died during childbirth, but it does seem coincident that we have an awful lot of these, and therefore it's probably more that at least a few of them are it's post-mortem bloat.
I find this really interesting because I don't understand what the evolutionary I suppose advantages of, like, because like if you look at modern sea creatures now, you think, oh, they lay lots and lots and lots of eggs, and this is how they become, because they've got the sea, so they just scatter everywhere, and that's this what fish do. I know that obviously whales don't do that, and dolphins don't have very many children either, but the fact that they're putting all that effort in, I mean, do we know why? Why would they be doing this?
Oh, that's such a good question. I don't know the whys to many things when it comes to marine reptiles. They're really fascinating groups, honestly, just in the speed of their evolution, how they evolved, aquatic features. So as far as why goes, it's anyone's guess, really. It could be for efficiency. Perhaps they were warm-blooded, or they lived in schools, and so there's a social aspect. So they were social enough that they didn't have to just lay millions of them because the parents may have protected them by living in family groups. And we do know that we do find ichthyosaurs kind of gathered together. There's a really amazing ichthyosaur site in Nevada called Berlin Ichthyosaur State Park, where we find tons of Shonisaurus ichthyosaur fossils all together. So that suggests, some social grouping behavior, maybe. So when you're social, you may not have to just, say bye to your young, never see you again. You can afford to kind of take time to, create this, offspring. But I'm actually not sure about the reproductive reasons why.
I just want to clear up for people listening in case they don't know which one an ichthyosaur is. The ichthyosaur is the one that looks like a dolphin, but its tail is the wrong way around. That's got a tail more like a tuna, but it's what I would consider. It's an old dolphin, even though it's a reptile. It's not a dolphin. Nothing.
Kind of, yeah. But I will say, a lot of people do think of ichthyosaurs as the dolphin ichthyosaurs. That's going to be kind of the ophthalmosaurid ichthyosaurs, which have been featured in programs like Walking with Dinosaurs. But ichthyosaurs are actually a lot more diverse than people realize, with some of them not actually looking like dolphins. Shonisaurus and Shastasaurus were among the biggest marine tetrapods that ever existed, being on par with whales in size. I believe Shonisaurus approached 50, 60 feet. Shastasaurus might have been even bigger. And these ichthyosaurs, for the most part, I believe, have been reconstructed to lack a dorsal fin. So they just had a smooth top of their body. And yes, an up-down shark direction tail fin, but huge. And there's something going around on Twitter the other day by a couple of ichthyosaur researchers I know, highlighting that Shonosaurus actually had teeth. So Shonosaurus had teeth. That means this was one of the biggest macro predators that ever exists, rivaling the sperm whale in size. And then there were also macro predatory, like definitely large, bone crunching, thing killing ichthyosaurs like Thalata archon, which did not look like a dolphin. In fact, they looked like mosasaurs. So ichthyosaurs were even doing the mosasaur thing millions of years before mosasaurs did. So ichthyosaurs are definitely much more diverse than most people who, if they're going to know ichthyosaurs, realize, just because those dolphin-shaped ones are so common and popular in the fossil record. But there are lots of forms. They were the first major marine reptile group to radiate into marine environments. So they had all that ecological and evolutionary radiation opportunity. So it only makes sense that you get tons of types.
So they were the first.
They were the first, yeah.
Of the 15.
Well, of the ones that so as usual with the kind of, we talked about this before, with the fossil record, the further you go back in time, the more fragmentary your data seems to be. Though, of course, the advantage of doing the marine stuff is to become a fossil, you've got to be buried. So starting in water is a good start compared to doing things like dinosaurs. But yeah, the Triassic in particular, the lineage is left, right, and centre. A lot of them didn't last very long in particular. But yeah, there's a whole bunch. And I think you were saying, because the really early ichthyosaurs, because we got some really early ones from China. And yeah, they're really, really long-bodied and more kind of eel-shaped, or, very big flat eel-shaped, but yeah, totally not that super streamlined dolphin or tuna body shape that, it's basically a lozenge with a couple of fins bolted on it.
Yeah, absolutely. And I know some of the work that Ryosuke Motani does on ichthyosaurs highlights kind of these early ichthyosaurs moving from this anguilliform type of swimming locomotion, which means eel-like, to a more thunniform, which is going to be the way tuna swim. The way tuna swim type locomotion. In the more the later Jurassic and the ichthyosaurs that actually persisted into the Cretaceous, we're going to keep that kind of dolphin thunniform shape. And that's another reason why that form of ichthyosaur is so pervasive, is because they also did last quite a long time. They went right up to the end, while the other big slender ones, the eel-like ones, the huge ones, and the macropredatory ones did die out sometime in the Jurassic.
So
I was going to say, sorry, Iz.
No, I was. If you're going to say something following on from that, that's cool.
It was vaguely related to a thing you said earlier, because you talked about the weird eyes, and so that's, Kirsten already mentioned Ophthalmosaurus, which is kind of the famous one for this. Some of these things had, like soup plate eyes, absolutely giant. And part of the reason, of course, is you see the big hole in the skull, but the other reason is they have these things called sclerotic plates that form the sclerotic ring, which is this bony things that sit on top of the eye. And I try to remember if we've mentioned this in an earlier podcast. We probably have. It's one of those things which humans see that and go, oh my God, that's weird. And of course, it isn't weird. Mammals are the odd ones for not having it, whereas birds have it and reptiles have it as well, and so it's much more common.
We discussed it before because you wondered if I might be able to see it in a raw turkey eye.
Oh, that was it. Yeah.
Because I was too grossed out trying to
try and get it. But yeah, Ophthalmosaurus, we're talking about 30 plus centimeter diameter eye, and we've mentioned this when we did the T-Rex episode. Basically, eye diameter is a really good correlate for eyesight, whether that's seeing fine detail or seeing in the dark. And so one obvious thing for a big divey swimmy thing, it gets really dark, really deep. And so having dirty grey eyes like the size of my head meant it could probably see really well deep down, which tells you that it's probably going after stuff deep down, which is pretty cool.
I've got a very quick question about the eyes. They must have had eyelids.
I have no idea. I will turn to my colleague.
Because I was just thinking, if you got that big an eye and you come and you're going down to the depths and you're coming up again, you're going to want to blink a lot to cope with.
Well, snakes don't have eyelids.
Snakes don't have eyelids. That's so there is precedent in other reptiles to not have eyelids. Whales do have eyelids, though they're not using their eyelids the same way we are. I actually just saw a really weird video on Twitter. It's beautiful but strange. It was a humpback whale coming up to the surface to look at someone on a boat. And I'm uncomfortable because I'm watching this like, oh, look at the water splashing into its eyes. But it didn't blink once, even as the surf washed over its eyeball. It was just open and looking at the person on the boat, filming it. And then it blinked, once very slowly, but it wasn't blinking to clear any debris or any water. It just seemed to be blinking in general.
Yeah.
So it's giving you a sexy wink.
Yeah, right, to the filmer. Yeah, but it was just really fascinating. I was like, I mean, it makes sense that a whale eye, if you're living underwater, may be just more impervious. Again, using its eyelids much more differently than we do. We do it to keep our eyes moist, to bat out any debris that falls into our eyes with our eyelashes. But whales, their eyes are always moist. So who knows? Maybe their eyelids are just a holdover from their ancestry, and they just have them. As far as ichthyosaurs go, when you compare them to whales, they're not going to need eyelids to keep their eyes moist. But I would agree that they may need eyelids to keep their eyes protected. So did they have them? Or that's something We will never
Yeah,
know, to be honest.
well, I mean, the protection, because when you think about sharks, famously the big macro sharks, they
Yeah.
roll the eyes
Yeah,
back in the head,
but no eyelids. Like,
right.
they just.
But that's the thing. But the protection is a big deal for a whale.
Yeah.
It isn't, because even things like sperm whales, their eyes who are going after big nasty things which could hurt them.
Mhm.
Their eyes are pretty tiny and they're not that crucial. But presumably something like Ophthalmosaurus, with an eye that big and it's going after big prey, the last thing it wants is a squid sucker or a random fish spine hitting that eye. So you'd think it would probably have to have one.
Maybe. But I mean, was Ophthalmosaurus going after prey that was that big? They're not particularly large ichthyosaurs. They had a smaller, slender snout, probably
That's
eating
true.
smaller fish, smaller squid. They needed that sight and that agility, hence their body shape. So I wouldn't peg it
I don't know.
to go after particularly large prey where it's worried about that kind of injury. Yeah. Oh, that's a good question. I've never considered the eyelids
Thanks
of
very much.
ichthyosaurs.
Well, you're very welcome.
Well,
I
for all
all
of
the
them, I
important
mean,
questions.
it's relevant for all of them, really. Again, there's a bunch of big macro predators out there that are taking big stuff.
What I want to ask a very obvious question now, which hopefully you will know the answer to, is were they breathing air or did they have gills? What were they doing?
Yeah, so they were breathing air. They probably had similar lung capacity timings as our modern marine mammals, whales and dolphins and seals and things like that. So yes, they were breathing air. That's going to be kind of a holdover from their terrestrial ancestry and their kind of general reptileness, which all have lungs. And so it is interesting that a lot of groups went back into aquatic environments in spite of having lungs, and they make it work. It's really amazing to me, just the lengths that some of these marine tetrapods that we have today can hold their breath and how deep they can dive, even though they're air breathers. It would terrify me. I would hate to be marine tetrapod, honestly, to pretty much constantly exist holding my breath. Like, that doesn't seem pleasant.
A good strategy.
But they do it well in there, and they seem content in their lives.
At this point, I have to remember. I can't remember which species or which clade it is. There's those freshwater. I'm pretty sure it's a freshwater terrapin group who have an alternative air source.
Oh, this is going to be naughty, isn't it?
Let me guess. Is it another orifice that can absorb oxygen?
Yeah. So there's cloacal breathing in a bunch of freshwater terrapin. Yeah, they do. They can.
Cool.
They stick their bum to the surface and suck air in, and they are doing some gas exchange from that.
Well,
they
that
don't have to bring their head up to breathe.
See, that's cool, but I don't think that's as cool as olive sea snakes. Olive sea snakes are, I think, the only known marine group that can actually absorb oxygen through its skin.
Oh, yes. I saw a paper on this not too long ago.
Lake Titicaca, the scrotum frog can do that.
But that's a frog. That's not a reptile.
No, that's true. Sorry.
I've seen a Lake Titicaca toad in Lake Titicaca.
Oh, that's cool. Oh, you're bragging. I see. You travel.
It is. It's one of the cool. Well, I'm not 100%. This is all going to get edited out. I have seen a frog in Lake Titicaca, and to my knowledge, there were no other frogs around there, and it looked a bit like the photo of a Lake Titicaca toad I could get hold of. So I think I've seen one.
They come in all colours, those things, brown, purples, and greens, but they've got really ridiculous skin. So that they can, for a large surface area, so they can do osmosis, which is the movement of molecules from a high concentration to a low concentration through a selectively permeable membrane. A star GCSE, thank you.
Wow, that was impressive.
Anyway.
Wow.
And then we're getting on to hairy frogs, which are doing that. But
listen, all. We're talking about amphibians. I explicitly excluded amphibians from my research scope because they're so wild. I don't have time for that. but so actually to bring up a point that you said before, how, some sea snakes still come on land, sea turtles, marine iguanas, extant compared to marine reptiles. Actually, and I'm gonna actually you, the olive sea snake is arguably the most aquatic marine reptile that ever existed. Olive sea snakes do not come ashore at all. They hunt underwater, they eat underwater, digest, and they, I believe they give birth to live young underwater. So the olive sea snake is fully tethered to an aquatic environment, which is similar to marine tetrapods, marine reptiles of the Mesozoic that were also tethered. The difference is that I give the olive sea snake an edge in marineness because they can absorb oxygen through their skin.
I guess the obvious question is, do we know that the others couldn't?
And that's a genuinely good question. I don't know. If I was given phylogenetic evolutionary relationships, if any group was through their skin, I would give that to the mosasaurs, only because they do have those snake-like affinities and they are lizards. They have that relationship. But this is not something, I genuinely don't think this is something that we could test ever in the fossil record, regardless of the stellar specimens that come out. So
no, that's what I was thinking.
But I would give it, if anyone were to do it, it'd be the mosasaurs, just based on phylogenetic relationships. That sea snakes can do it, so maybe mosasaurs could.
But my thing with those kinds of things is it always gives you the possibility. Like, if we'd never seen this in any extant reptile, we, I think correctly, completely rule it out. But the very fact that at least one has done it shows that it is possible. And therefore, when you've got 170 million years of evolution in a dozen different groups, yeah, probably one of them managed it.
Yeah, that's true. I mean, the chance and the opportunity, it's just amazing sometimes when I think of the scale of time. And you know, the way we casually talk about it, like, oh yeah, you know, the ichthyosaurs did it, then the plesiosaurs and the mosasaurs, you know, they have this variation, whatever. It's like, of course they did. I mean, just they couldn't not.
Yeah.
So what I find particularly fascinating, though, about marine reptiles and marine tetrapods in general is how it took until the Mesozoic for it to happen. We really fairly confidently believe that there were no major marine tetrapod radiations in the Paleozoic.
Yeah,
with the exception of mesosaurs, and mesosaurs are considered the first secondarily aquatic tetrapod, but they didn't evolve that in kind of highly aquatic, well, I guess aquaticness, if I could use that as a word, as ichthyosaurs would, but they were semi-aquatic. They had flattened tails, they had big frog legs, looking frog legs that they probably used for some type of propulsion, but never became marine. That took the end Permian extinction to reshuffle some of these ocean faunas for terrestrial reptiles and amniote groups to say, okay, well, now's our chance. Yeah, and there are some other Paleozoic groups that may have done it. For example, Spinoaqualis, which is one of the earliest reptiles, may actually have been semi-aquatic. So, but
Okay.
you know, yeah, there are limitations to length of fossil record. You know, the further back in time you go, the harder it is to recover these types of fossils, even though they're going to be aquatic. So, like you said before, if you're going to be swimming around, I would give you a higher chance of being fossilized to begin with. And so the fact that we don't have many Paleozoic secondarily aquatic groups in spite of that does to me suggest that, yes, the Mesozoic is where this really took off, where amniote groups were like, all right, we're going back to the water. We're sick of this.
One thing I want to pick up on, because just as a kind of point of order, so you just said, you know, the mesosaurs were fresh water, and we've been saying marine reptiles, like all these things, just lived in the sea and never entered freshwater systems, and of course that's not actually really true at all. You know, a lot of the most famous and the biggest ones were absolutely living in the sea, but a whole bunch of these are estuary dwellers and would be in rivers and lakes and things too, and we haven't really mentioned that.
Yeah, and so that's the thing, is when you're an air breather, you don't have to worry about chemical differences, osmotic differences in the water as if you would have gills. So we have, I believe it's Hell Creek.
Good name.
I think they have a plesiosaur.
So American.
Yeah, they do.
Yeah, Hell Creek is a terrestrial environment with freshwater systems, fluvial systems. They have a plesiosaur, and you know, it makes sense. We don't really know the life histories. For all we know, some groups of plesiosaurs, even ichthyosaurs, were coming in, having their offspring in freshwater environments before they would mature and move out to sea, which many modern groups do, like bull sharks. And then there are mosasaurs that have been found in freshwater environments too. So that's the thing, is the assumption that these are marine tetrapods is because we find a majority of them in marine sediments. But as far as evolution goes, it doesn't necessarily mean that all of these groups, when they started their evolution, were near shore groups. That they probably, and this is not based on any particular subset of research or papers, but I mean, a lot of these groups probably, when they first were starting out, were freshwater, fluvial, river-based, lakes, things like that. I mean, we know that for whales. We find early whales in freshwater systems. I believe Ambulocetus is found in, this is early walking whales, what it means. I believe Ambulocetus is associated with freshwater sediments. I will double check that, actually.
I think Indohyus might be, which is one of the earliest ones as well, which really isn't much of a whale and more of a big rat. But...
Yeah, it really is.
Well, and similarly, today we've talked about big marine turtles and freshwater terrapins, but I suspect a lot of people don't realise that all the big crocodile species are quite happy in the sea, and will swim big distances. Not necessarily across oceans, but the American crocodile, American alligator, Nile croc, the New Guinean croc, Philippines, and the big saltwater one, all happy in the sea. There's a freshwater seal in Lake Baikal in Russia, and there's 3, if not 4, lineages of freshwater dolphins, though the Yangtze is probably extinct now. And then we've got manatees and dugongs, which are freshwater and marine, depending on which species.
Yeah.
So yeah, the freshwater or aquatic, you say tetrapods, limbed animals going back to the water, they don't have this fish thing where they usually either adapt to the sea or adapt to rivers and don't really switch. These things almost certainly switched, well, on an individual basis during their life cycle, but entire lineages were probably appearing and disappearing and moving between systems.
They had the ability to. We definitely know that if they want to, individual decisions, extant animals today we see all the time doing a weird thing compared to the rest of the whole clade. Yeah, and so I personally, in my research, where I study both marine reptiles and marine mammals, I actually just refer to them as secondarily aquatic groups. I try to stay away from using the word marine, unless it's a very obvious marine one, like extant whales as an example. But yeah, but marine tetrapods, secondarily aquatic tetrapod really are synonymous, regardless of the wording behind yeah, exactly. Yeah. Biology is funny like that. Nothing is what we think it is. Humans, we want everything to be in a box, but it just is not. So marine tetrapod is a safe word for sure, and people know what you're talking about. But when you really get down and dirty with it, it's like probably not actually marine. But yeah, it's cool though. And if you're gonna, as a lineage, as a clade, make it to marine environments, then that is going to suggest that you are going to be particularly aquatic. If you're gonna venture into the marine environment to start.
Do you get any of these which are obviously herbivorous?
Oh, so that's a really cool thing about marine reptiles compared to marine mammals. Marine reptiles were really carnivorous, like by and large. From what we can tell, there weren't big, and there probably were some, I can't think off the top of my head, there weren't like big filter feeders. And of course, baleen whales aren't necessarily, they're not herbivorous, but they're eating krill. But most marine reptiles were eating things. I mean, like eating animals, like mosasaurs. You had mosasaurs like globidens, which had these big shell-crushing teeth that are likely, and we're very confident in this, were eating ammonites. And so that's they're eating a large animal. Other mosasaurs.
We get ammonites with these rows of holes through the top and bottom, and it's like, well, you know what happened.
Something tried to chomp
they
that.
They do look tasty.
It's like calamari.
Yeah, I was gonna say calamari.
They're like, Danish pastries or something.
Oh, yeah.
Oh, yeah, that true. I was thinking more shelled calamari or like octopus sushi, but yes, the pastries works. Now I want a pastry.
That's very true. Well, on the subject of crushing placodonts, which are just insane. So
it's a good name. I like this name. I've never heard it before. Placodont.
Yeah, placodont. So basically the flat or armored teeth, and they've got these huge flat crushing teeth in these weird little short stubby skulls with kind of little pokey snouts. Anyone who knows this, you get a bunch of long-nosed terrapins. They kind of have this extension nose. But there's a bunch of placodonts which are kind of a bit tubby, quite frankly. They've got a kind of big round body. But some of the later ones are just like turtles, but not turtles. They're really, really flat with a giant shell, just like a turtle, only they're not. There's something completely different, which entirely independently has got 4 giant flippers and a giant flat shell, but they dive down and are eating clams and mussels and stuff like this and smashing them up with these unbelievably big teeth in these tiny little heads.
Yeah, placodonts are absolutely bizarre. But as a good example, even some of these really bizarre looking marine reptiles, like as far as their diets go, we're still eating things. In fact, sea turtles are probably the only confidently herbivorous groups of marine reptiles. But, other mosasaurs that weren't globidens were eating fish. We're eating hesperornithines. We're eating plesiosaurs. We have these stomach contents. And then...
What is a
Well, the fun thing about hesperornithines is we're talking about all these secondarily aquatic reptiles. and technically
They count.
this is a secondarily aquatic reptile.
Yeah.
They're birds. They're relatively early birds, which immediately went back to the sea again. They gave up flying, became flightless. They look a bit like
Like a
they look a bit
cormorant.
like cormorants or grebes, but they have tiny little wings, and they were swimming using their feet in the way that grebes do. So they were paddle-like, almost frog-like swimmers with their back legs. And some of these were big, like 2-3 foot high.
Okay. I'm just going to take your word that you're not making all of this up. Carry on.
Yeah, but that's what's cool is they are marine reptiles. And it's funny, I actually, one of my committee members is a very famous bird kind of focused paleontologist. And he is only slightly, and I say that sarcastically, slightly perturbed that I do not have birds included in my research. I had to focus in on quadrupedal groups that evolved to aquatic environments because there are so many birds that became secondarily aquatic. Truly, it just extant living birds. Oh my gosh, I could go forever. You have cormorants, you have loons, you have grebes, you have penguins, you have auks, which are dead, but they're different, and pelicans, even birds, guillemots, like
blue-footed boobies. Yes. That's all I want to say.
Yeah, or ducks, like, and one could argue that enceroforms are also secondarily aquatic groups. Some birds today, as far as marine reptiles go, are about as aquatic and as tethered to the environment as some of the earlier semi-aquatic marine reptiles that we have in the fossil record. So I couldn't do it. I couldn't do birds. Birds is a PhD on its own, but they are marine reptiles. Birds are definitely marine reptiles. They did it differently than a lot
particularly
of
the Hesperornithiforms, because they're right there doing it alongside these other things.
Yeah.
Did the Hesperornithiforms
very good.
Very nearly. Did they feathered?
Yes, yeah. And they had teeth, and they had teeth too. Like they had beaks with teeth. That's what made them also cool.
Just imagine a really big cormorant, but strip the wings right down and make them a bit bandy-legged, and that's pretty much it.
I mean, it's cute. Yeah. It's really cute.
Yeah,
and with the goofy teeth as well. I like it.
Yeah, they're funny things. But going back to that earlier point about these being carnivorous, I mean, an aspect of that is the fact that most things in the sea are carnivorous. I think we don't get that because we are terrestrial and we're so ingrained into that. There's a tree and it's eaten by the deer, which is eaten by the wolf. And that's it. We have kind of 3 layers or trophic levels, to use the ecological term. In the sea, it's really, really common to have 5, 6, 7 trophic levels. You have some phytoplankton, and that's eaten by zooplankton, so that's your second one. That's eaten by krill, and that's your third one. And they're eaten by sardines, which is your fourth one. And they're eaten by some mid-sized fish, which is your fifth one, which are then eaten by seals, which is your sixth one, which are then eaten by sharks.
Yeah.
And so you've got 6 levels of you've got one plant, 1 herbivore, and then 5 predators. So yeah, most things are predators.
Yeah, and they're really interwoven too. Like thinking about food webs, like marine food webs, they are just a mess. Like I've seen papers that have marine food web figures. I'm like, why did you do this? You didn't have to illustrate the chaos.
Everything to everything else. Yeah,
and it is fascinating. And of course, marine environments don't have the degree of vegetation that we kind of interpret on land. Like you have kelp and algae and seaweed and things like that, and seagrass, and so things like manatees and dugongs really occupy that niche of munching on seagrass and things like that. But yeah, that's a good point, that they were mostly carnivorous, but it is in slight contrast to like marine mammals of today, which, sure, I guess filter feeding is technically being a carnivore, and for example,
it's also not quite the same
exactly
thing.
and then the manatees are doing that, but of course there's not that many marine mammals compared to marine reptiles. Oh, and then aquatic sloths, secondarily aquatic sloths, are absolutely herbivorous. So it's just interesting that the marine mammals still definitely did the herbivorous thing more than the marine reptiles, even though, yes, by and large, these marine groups are 1,000% carnivorous, compared to others.
Getting off topic, what were now the names dropped out of my head.
For
the
which?
The big fat like hippo things that aren't quite hippos from the Caribbean.
Desmostalians?
Desmostalians. Yeah. What, are they herbivorous based on their skull?
Yeah, I think so. I believe they're herbivorous. Also based on their evolutionary nesting. They're kind of yeah. I think
it's off topic. I was just curious. Isn't that another one? And so we got another herbivorous lineage.
Mm-hmm. Yeah. In marine
mammals are a bit rubbish, clearly.
maybe a little bit. I do have a natural bias.
Okay, so the KT extinction, big asteroid.
It wasn't a fun time.
But I could kind of see, all the fish didn't go extinct,
Yeah.
and all the birds didn't go extinct. Dinosaurs who were birds did go extinct. And why did all the ones in the reptiles in the sea seem to die at this point when the turtles didn't?
That's a really good question, and to be honest, I don't know. I believe I think the first I know, right? It's so disappointing. So I do have some ideas that come around. So the cool thing about sea turtles, our extant living sea turtles, is that all of our modern sea turtles, I believe, are secondarily derived from a freshwater turtle that survived.
Yeah.
So it means that even sea turtles survived, but they didn't survive as sea turtles. They survived as freshwater turtles, which then in the Cenozoic radiated to become our extant sea turtles. So our living sea turtles are not related to those Jurassic sea turtles that first evolved. They're secondarily sea turtles. So the freshwater environments, the freshwater reptiles survive. So crocodilians survive for the same reason. So freshwater was a little bit more protected and insulated from the completely devastating effects of this asteroid. Marine environments are exceedingly fragile. They really serve as the foundation of the global ecosystem. And they're very tethered to terrestrial ones as well. And when you block out the sun for a couple thousand years, and you have debris coming in, the finite, and we just talked about how little vegetation there is in aquatic environments. So if you have no sun, you're going to completely wreck all of those photosynthetic systems in aquatic environments. And so that's going to, literally from the bottom up, just completely wreck again these marine trophic systems. So I think that's why these marine groups went extinct, even though they were big and they seemed, super impervious. Mosasaurus, some of the biggest marine predators that ever existed. They were tough. How could they go extinct? Same with groups like elasmosaurs. But they probably had a prey problem where the survivors in these aquatic environments were competing with them for smaller prey. Things like sharks. Sharks obviously survived, and some of them were pretty big, like even right after the extinction. Could probably edge out mosasaurs and other large marine reptiles.
They need to hold their breath.
Yeah, and there's that. And so it just, the oceans probably did not respond very well to the asteroid effects, basically, and probably as bad as land, if not worse. So.
And related to that, big things generally struggle. When food is short, the biggest stuff is going to suffer the most, and that's mostly what a lot of these groups
and
were.
That's such a good point. And there is research on that. People who study mass extinctions in general, the small survive. And so, so even if you just take it that simply and not kind of like try to parse out the minutia of what the asteroid would do to the ocean, it's just a size thing. Marine reptiles, we love them because they were huge, and that was probably their downfall.
What will feed an elephant for a day will feed half a dozen mice for months.
Mm-hmm.
And of course, if you only feed that one elephant, you still haven't got a population at the far end of it. Whereas, a dozen mice can live off an apple a day. You don't need that much food to keep everything going at the small scale. It's not like the KT extinction took out all of these secondary aquatic reptiles, because a whole bunch of them had gone extinct in the Triassic and others went extinct at various times. It's not with the dinosaurs, most of the groups appear early on, and then there might be a few late stragglers, but most of them are actually still hanging around by the end. But that's not the case with this stuff, is it?
No, and so trying to think. So a lot of marine reptile groups did make it right up to the Maastrichtian. They were in lockstep with dinosaurs that went extinct, but mosasaurs really dominated kind of those late Cretaceous faunas.
But didn't plesiosaurs go extinct in the late Cretaceous, but not at the end Cretaceous?
No, actually, elasmosaurs went right up to the end.
Okay.
Yeah, and so that's the thing when it comes to
it's still there in the Loch Ness Monster.
Yeah, exactly. But so the thing with marine reptile shuffling is you can kind of look at it as, like, I guess, the dominant time per the major three. So ichthyosaurs, plesiosaurs, mosasaurs. Ichthyosaurs were the first, and the Triassic was probably ichthyosaur, sauropterygian, which is the group that includes plesiosaur, dominated. Then the Jurassic was big ichthyosaurs, big plesiosaurs, and that's where plesiosaurs diversified into pliosaurs. So these are going to be those big, short-necked kind of plesiosaurs, like like Pleurodon, which is pretty famous household name as far as a pliosaur goes. And then other kind of shorter necked plesiosaurs like Dolichoryncops and polycotylids and other groups of plesiosaurs like that. Then you had some major climatic events towards the end Jurassic, and we lost a lot of ichthyosaurs. Ichthyosaurs did not like the climate change, whatever was happening. Plesiosaurs were pretty good. They were pretty solid after these kind of Jurassic climatic events. But even their diversity was a little bit more winnowed as well. And so the kind of dominant marine reptiles for the early Cretaceous were kind of plesiosaurs, really. You had those, still had those big short-necked pliosaurs. And then you had elasmosaurs, which evolved sometime in the early middle Cretaceous.
For people who don't know, elasmosaurs are the famously really long necked
super long necked ones.
When that kind of stereotype of the big curly neck coming out of the water grabbing stuff, which they're probably not doing, but those are the elasmosaurs.
Yeah, but then pliosaurs went extinct in the Cenomanian, so this is also what is a Cenomanian?
That's what I think I'm thinking of, is that the pliosaurs went, but not all plesiosaurs.
Yeah, so the pliosaurs bought it, and it is no coincidence that after the pliosaurs died out, mosasaurs entered aquatic environments. I mean, mosasaurs and pliosaurs, I see people mix them up, because they look very similar. Mosasaurs, of course, have a much longer body, longer tail, but they were giant, big-headed macropredators. And so mosasaurs had this opportunity, this niche that they were able to fill after the large pliosaurs went extinct. But then mosasaurs and elasmosaur plesiosaurs were kind of the ones that were making it to what they didn't realize was the finish line, the Maastrichtian. But then there were some ichthyosaurs as well. I believe the ophthalmosaurids, or the broader group that includes those dolphin-looking ones. I cannot think of them off the top of my head. I'll Google it, actually. Also made it to the end as well, but weren't big players because they weren't giant macropredators. So it really, as far as the fight goes, it was between the elasmosaurs and the mosasaurs.
And were they all giants, or were there little species?
There were some small mosasaurs, like halosaurines, were smaller.
Yeah, but how small is small? Are we talking like, I'm thinking like beaver size?
No, definitely. So the earliest mosasaurs did start out probably about a meter. They were probably the size of our modern monitor lizards, like our average monitor lizard, not too big. But when groups evolve into aquatic environments, they get big fast. So I don't really think we have a lot of intermediate mosasaurs that are between, that 1 meter long early mosasauroid called Agialosaur, and then like the next biggest or next smallest one, like halosaurines. Oh, actually, that's not true. Dallosaurus, which is found in Dallas.
Where's that from?
Yeah, exactly. Is a kind of primitive mosasaur. It has what's called this plesiopelvic or plesiopedal pelvic girdle where the back hind limbs attach, indicating that could probably still come in and out on land. That was pretty small, probably less than 5 feet, but then after that they got big.
I know what Dave is going to say. He's going to say it, but of course they were small at one point in their lives, and that's how they fill in those gaps in the environment.
That is always part of it, but it also it's just this common form of confusion, is people will see small fossils and go, oh, well, there were small ones, and it's like, well, most of the time those are juveniles. But one thing I want to say, because talking about mosasaurs, you might know better than me. Izzy might want to edit this depending on how it goes, but are they true varanids, or are they varanoids, or are they just generally around that bit of the tree right now?
And what is a varanid?
Well, I'll get her answer and then I'll re-ask the question.
So varanids are going to be monitor lizards, so Komodo dragons, Nile monitors, savanna monitors, ackies. Many are popular as pets, and they're among the biggest lizards, they are the biggest lizards that we have today, and they're all predators, and they're really cool. I will say that. But mosasaurs, I believe the current consensus, and there is a little bit of a butting heads, it's not a vicious scientific, feud or battle compared to some others, but mosasaurs are actually probably sister to snakes. I'm in the mosasaurs as sister to snakes camp.
Oh, are you? Okay.
Yeah, this research was kind of spearheaded by people like Michael Caldwell, and it has been phylogenetically verified by multiple researchers, character-based stuff. And so what this means, of course, you're probably thinking, well, snakes have no legs. Mosasaurs definitely had legs, and they definitely did. We see their limbs. So it probably means that mosasaurs split from the ancestral snake when snakes had legs. And we know that snakes had legs. They are lizards. We have fossil snakes that have legs. So that's kind of the current. I think that's the consensus. I know there are some people who still say no, mosasaurs, they're clearly sister to varanids, but it doesn't matter. They're also varanids themselves are also very close to snakes. So it's, I'm not going to say it's petty. Knowing is a cool thing in science. It's worth exploring. It's not worth just kind of, brushing off and saying, oh, who cares what mosasaurs are closely related to. But whether or not they're more closely related to snakes or varanids doesn't matter in the context that they were lizards. They were deeply nested as lizards. And that's what makes mosasaurs, to me, so cool as far as marine reptile groups. For anyone.
And that means basically you're giving the complete go-ahead to any paleo artist that a flicky outy tongue.
Yes, and that's so good. They definitely had forked tongues, 100%, and they probably were using them the same way. So
I was going to say, do they have a vomeronasal?
They do. They do. They have the bones. We know there's. I'm not a mosasaur cranial person. I'm not going to be that confident in what I talk about. I like the rest of the mosasaur after the head. If you gave me mosasaur with the head chopped off, it would be perfect for me.
Hang on. I think I probably need to explain what a vomeronasal organ is.
Yes.
Oh gosh. It's something that lets you know it's got a forked tongue.
Yeah.
Right. So Kirsten just said, they're doing the same thing. So when you see a snake or lizard stick its tongue out, I think you often see this on the documentaries. They go, oh well, what they're actually doing is they're smelling with their tongue. That is true, but what they're actually doing is they're sticking the tongue out. They're basically gathering scent particles from the air. They then pull the tongue back into the mouth, and then they push it up into the roof of the mouth. And that is the vomeronasal organ. Yeah. So vomers are the bones in the roof of your mouth, and nasal is your nose. So the basically receptors are in the roof of the mouth. And that's what the tongue flicking is doing.
Yes, it's also called the Jacobson's organ. That's also a common one that people might hear about. Cats have one too, by the way. Actually, a lot of animals have one. So mosasaurs definitely had forked tongues, and it's not impossible to think that they were using them for scent. Sea snakes gather scent with their tongues. You see sea snakes, they're so cute. Actually, sea snakes have the cutest little tongues, but they flick their tongue out. It's actually, they flick their tongue out a lot shorter than terrestrial snakes. That is a really interesting feature. In fact, when you look at sea snakes flicking their tongue, you can barely see it. Basically, only the fork part comes out, does a little flicker and comes in. I believe it's because scent is a lot denser underwater as far as the particles go, so they don't need to get more surface area, where like a cobra has to stick its tongue out way far, practically flicks it. Sometimes it hits the top of its head with the force that it flicks the tongue. But so if mosasaurs were flicking their tongues, which I believe they were, they probably weren't sticking them out so far, probably mimicking kind of that sea snake look. And another cool thing about mosasaurs, as far as their similarity to snakes and lizards, is they had a second row of teeth. Also, we also have that, those palatine teeth.
I had that for a while as a teenager, when my baby teeth hadn't fallen out.
Oh, that's cool, actually.
Yeah. And then they fell out, and it was very upsetting. Mm-hmm. And now I have normal human teeth. What else should we be asking, Dave? Because we've had you for ages now. This is brilliant. What's a good question that we should be asking?
What should we ask you?
I didn't touch on some of the more obscure marine reptile groups, like I didn't. So there were tons of other marine reptiles that evolved into aquatic environments in the Mesozoic, in addition to the big three. Some of them have modern relatives, like marine crocodiliforms. You had metriorhynchids, which are really cool because they're crocs that pretty much did the mosasaur thing. They evolved tail flukes, streamlined bodies. Something interesting about them with their morphology is that they actually had really large hind legs, which is very bizarre. Big paddles, which is strange because crocodiles that we have today were definitely axial swimmers. And so axial means you're going to be swimming with your spine and your body column as opposed to your limbs. So, and they had the tail fluke. They probably were swimming with their body and tail fin, but again, they did have these big, weird frog legs. So that's strange on the marine croc side, but they were marine crocodiles. And so this broader group, I guess, is called Thalattosuchians. Thalattosaurs, which are no relation. Thalatto, I believe, is a prefix having to do with the ocean, like thalatto, thalasso. And so you have thalattosaurs, which were these little marine semi-aquatic groups that are kind of unsung, that evolved in the Triassic. They were kind of overshadowed by the the Sauropterygians and plesiosaurs and the ichthyosaurs, but they existed. They were small. They were very small, though. Little. They had flattened paddle-based tails. They were definitely in aquatic environments of the Triassic.
Well, phytosaurs I was going to mention because they're the one that I look at occasionally. So phytosaurs really look like crocodile.
Yeah.
Their name means plant lizard because apparently when they were first discovered, someone thought they were herbivorous, despite the fact that they really, really look like crocodiles. I don't know what bit of them they found that they didn't spot that these things were basically crocodiles.
Maybe they found a gummy one.
It could be, but it
looked like a duck.
It's still one of the most misnamed groups of animals. These,
and there are many.
Yeah, big long nose with loads and loads of spiky teeth in them, and very crocodile-like, but only in the Triassic.
Yeah, in the Triassic,
and only in the late Triassic. So they go at that end Triassic extinction.
Yep, and then I'm trying to think phytosaurs. I always forget.
Pachypleurosaurs.
Pachypleurosaurs aren't they? They're Sauropterygians, right? So it's just kind of that. So for those listening, Sauropterygia is going to be.
We have thrown a lot of names around today.
Yeah, it's referring to that broad group that includes plesiosaurs and their relatives. So the earliest Sauropterygians are going to be nothosaurs, pistosaurs.
Oh yeah, nothosaurs. There's another.
I believe pachypleurosaurs are Sauropterygians as well.
Yes,
if not,
are.
Yeah. So those groups. So yeah, and then Sauropterygia would eventually give rise to Plesiosauria, the highly derived Sauropterygians. But then there were also in the Triassic Tanystrophiids. How could I forget Tanystrophiids?
Yeah.
My first paper was on Tanystrophiids. Yeah, Tanystrophiids are wild because we think about...
If you want a neck, we've talked about elasmosaurs, and we've talked about mamenchisaurs for sauropods.
Yeah.
Tanystropheus and its relatives...
They want neck. Yeah. they want a neck.
Just a neck?
They are mostly neck. They really are. Their neck was longer than the body and tail combined. And what's interesting is that they were semi-aquatic. And so it's bizarre to think of how this neck would have been facilitated in an aquatic environment. I don't know, but all I know is that in my own research included is that Tanystrophiids with these exceedingly long necks seem to be tethered to aquatic environments. My research was describing a Tanystrophiid that was found in fluvial sediments, so freshwater sediments, where Tanystropheus is typically associated with more marine. But regardless of marine versus freshwater, and we touched on that before, like if you're an air breather, that chemical difference doesn't matter. It's just about your ecology and what you're eating. They clearly needed water to support their long neck, and they probably were rowing with their back legs. They also had these big, what I call these frog legs, with long hind feet. That's the word. Their feet were long, probably had webbing, and so they're probably swimming with their back legs.
They have fairly long tails, though, don't they?
Pretty long.
It's not like they've got a stumpy little thing like you get on some of the big plesiosaurs.
Right.
There's a fair bit of tail there.
It's less stumpy than a plesiosaur, but it's not as long as a lizard. In between, but it didn't seem to have any paddle-based adaptations, no lateral flattening, no dorsal ventral heightening that you typically see in groups that are going to start to use their tail and their body for paddling. So they did seem to be what are called paraxial swimmers, so a limb-based swimmer. So I think those are the big groups. Crocodiles did it again in Dinosaurids. Weren't they Cenozoic? I know they're right on the margin.
You're on to tell me this stuff, not ask me.
I'm going to say they were definitely.
I definitely know the name Dinosaurs, but I don't know
They wrote every day, the Dinosaurs.
Okay, no, yeah, they were late. Yeah, they were late. No, it says here. This is Google. Yeah, Dinosaurs were Neosuchian crocodiliforms, so they were not the Latisuchians. They were more closely related to our extant crocodiles that lived from the late Cretaceous and the Maastrichtian to the Eocene. So they were
went over the boundary.
So they made it over the boundary as secondarily aquatic groups, and fairly large. As croc size goes. There's another group of marine reptiles that was right after the end Cretaceous mass extinction. Paleophis. It was a giant sea snake, like a sea serpent. Scary animal.
I've just remembered Champsosaurs.
See, there are so many. Oh my gosh! Like even me, I don't have them all organized in my head. They just keep going.
So Champsosaurs are another group which look like long-nosed crocodiles and were hanging around mostly in freshwater and eating fish. But they are a group which absolutely get over the KT extinction. Yeah. So they're really common in loads of late Cretaceous ecosystems. When I go up to Dinosaur Park in Canada, which I've done plenty of times, you find Champsosaur bits absolutely everywhere. But they make it over the KT. Yeah. So another group who, at least initially, were a freshwater semi-aquatic animal that actually survived. So as we were saying earlier, that general pattern is fairly common.
I don't suppose either of you know about whether any aquatic marine reptiles who happen to be birds and dinosaurs that made it over the KT, or did they only dinosaurs survive through birds as smaller?
As we've just kind of said with all the other stuff, most of the birds didn't make it over. So that, again, there's this, I think, slightly false impression that like the dinosaurs died out and the birds survived. The birds took a massive kicking as well. There were loads and loads and loads of bird lineages, and most of them went extinct. There was a paper only a couple of years ago now that did a fairly good analysis of this, because there are at least some groups which we're finding on both sides of that boundary, or at least relatively close relatives, and it suggested that it was actually a bit surprisingly in that context, it was some of the more terrestrial birds, and by that I mean running around on the ground rather than perchers, that did best, which is a bit of a surprise, because I think the conventional wisdom was that if you can fly, or to more accurate, if you're a really good flyer, in other words, you're a gull, say, or a blackbird as opposed to a chicken-like or grouse-like thing, then everything's really, really horrible, but I can fly really well, so I can fly around a bit, and all that place over there 20, 30 miles away looks a bit better. I'll fly that way. And obviously, if you're a chicken which has to run to power off the ground, and after the first 10 yards you're running out of puff and you're a bit knackered and you could do with the rest, that's not an ideal mechanism to get to a nicer place that's not dying horribly. And yet, actually, it is those, inverted commas, ground birds which seem to have, on average, done better than the good flyers or the early water birds. Yeah. So it is a bit counterintuitive in that front.
Well, see, I don't know. I think that makes sense personally. And I get the notion, the idea of like, oh, well, you can fly to better pastures, greener pastures. But I find that if I was to handle an apocalypse, as an example, I think...
if I were a bird.
Yeah, hunkering down. I feel like hunkering down and being nearer to the ground, especially in extinction, you're burrowing, you have all this, detritus that's around you, and you're able to, survive off of it. I just feel like the hunker down method of ecological being, so closer to the ground bird, is going to be a little bit more resilient than one that is trying to flitter around and find the good, especially when it's a mass extinction. There's not a lot of good to go to, and instead you're wasting energy getting to that potential good. Yeah.
Snakes, though.
Yeah, I mean, in my head, I'm thinking kind of magpie.
Yeah.
Eat just about anything.
Yeah, that's true.
But again, there's not necessarily eco space for all of those.
Right. Yeah, but then, so to answer your question, to start out, did any of these, I think you asked, any of these aquatic birds survived over? Not really, but I will tell you that the duck lineage, and Anseriformes and Galliformes are among the oldest extant bird lineages, are really old, like incredibly old, and ducks did the duck thing pretty fast after. Yeah.
There's the inverted commas Cretaceous duck.
Right.
Which is...
Yeah.
Oh, yeah, the wonder bird.
No, that's the wonder chicken. So yes, there was a fossil described just last year, 18 months ago, which has been dubbed the wonder chicken, and I know one of the authors of that, Albert Cheng, listens to this, and I'm sorry, but I think wonder chicken is a terrible name for this thing, and he's going to be annoyed.
It's brilliant. I think it's brilliant. I remembered it, didn't I? Yes. I'm not going to remember anything else, am I, today?
It's a personal opinion.
Yeah, but doesn't wonder chicken have duck-like affinities too, given its age?
It's got duck back legs and a chicken head.
Yeah.
It's a gallo, and so there's this group Kirsten's mentioned a couple of times. There's the gallo Anseriformes, which I know is a horrible name, but Gallo from chicken and Ancera from duck, actually there is a big lineage of birds which is the ducks and chickens, and therefore associated things like grouse and pheasants and turkeys are all in the chicken thing, and all the geese and swans and things are in the duck thing. They all form one big lineage, and they are absolutely around in the Cretaceous, as in the ancestors of that collective group. But there is, I think it's one femur, so one thigh bone from, I want to say, China that was described as possibly being on that definite duck side, and therefore there would be duck-like animals in the Cretaceous. And if that's true, then ducks obviously did survive the Kate extinction, because we sure as hell have them now.
Yeah, it's weird. I mean, I love ducks, so I'm partial to ducks. I want to hear all the cool things. Yeah, exactly. Well, a lot of people don't like ducks.
Apart from the fact that they're, homosexual necrophilic gang rapers. Yeah. But anyway,
mine is that.
Apart from that bit, I have a non-scientific scientist theory. It's my theory. Ground nesting birds, like chickens, can lay eggs all year round. Flighting birds tend to lay eggs seasonally. Therefore, if you can lay more eggs and have more babies...
Is that chickens do that in captivity, though, rather than ground nesting birds do that?
Don't know.
Because I doubt
know
the
nothing
grouse
about
are laying
this.
eggs all year round on the grounds that they live in Scotland.
Right, like didn't we...
Bloody miserable.
Didn't we select
if grouse lived in like Spain, they'd be fine. But they can't do that because of foxes and that.
Yeah.
So before the mammals get their act together, they can lay loads of eggs. It's fine.
Yeah, I know nothing about.
Like I said, I did put my
laying.
non-scientific hat on before I said that because I knew it was stupid. All right then, we've got plenty here. It's going to take me ages to edit this. I hate you both. And this is the big thing, Dave, right? Dinosaurs are not birds. So, what makes a bird a dinosaur? What makes a dinosaur a bird? And I know we've covered feathers, but do they have anything else in common other than, just being fluffy?
Birds are dinosaurs. Dinosaurs are not birds. So, humans are mammals. Not all mammals are humans. So one sits within the other taxonomically. And feathers, we've talked about feathers a lot. We now have dozens of different species of dinosaur which have definitive feathers. We have a bunch of others which have feather-like filaments, which may or may not be feathers, and has some interesting questions for their evolution. And obviously that is in itself an extraordinarily strong line of evidence to associate birds with dinosaurs, or to link the two together. We don't see any other species with these or any other lineages with these features. We do see that. But there's lots of others as well. And obviously, kind of first and foremost, when you're dealing with vertebrate paleontology, we have the skeletons themselves. And there are a bunch of traits in the skeletons that we see in birds and we see in dinosaurs, or at least some dinosaurs, that are not seen in anything else. A really neat one, which is always worth talking about, is a thing called the semi-lunate carpal, or occasionally hemilunate carpal.
The hemilunate carpal. Oh yeah, like carpal tunnel syndrome. Carpal tunnel syndrome is where you can't type anymore because you've been typing too much. I know things.
Yeah. So you have a bunch of bones in your wrist called carpals, and a semi-lunate one is a half-moon one. That's literally what it means. So it's a kind of half-moon shape or a semicircle. And this is a really critically shaped wrist bone, and basically you see it in things like dromaeosaurs, so Velociraptor and its relatives, and you see it in Archaeopteryx, and you see it in various birds, and you don't see it in anything else. And what it allows the wrist to do is to fold back against the arm.
Yeah, this is the trick of being able to touch your little finger to your forearm.
Yeah, if you hold your hand up and then kind of point it down as if you're doing kind of a karate chop, and then keep going. Birds and a lot of the things nearest to birds, because of the semi-lunate carpal, can keep rotating until not their little fingers, they don't have one anymore, but that side of the hand will end up pointing backwards along the arm towards the elbow.
You can't wrist lock 3 them, Jitsuka, in the room. This is, yeah. There's a wrist lock called Kotagatami, which is what I know as that. And you can basically get somebody to kneel down before you and hit their face on your kneecap if you're good enough. Just with a simple flick of the wrist that way, because you literally cannot bend that way.
Yeah, and so you often see both illustrated and then in movies dinosaurs having what people often call bunny hands. So they kind of flop over like a little bunny rabbit, because obviously the actors or the puppeteers in the suit can't bend their hands backwards. But that's what birds do. And it's a really important part of the wing stroke, but it's also very useful for just kind of getting those big long arm feathers out of the way and tucked up. And so this is something which evolved before flight. I wrote really quite a cool paper on this. There's a colleague of mine called Corwin Sullivan, who's Canadian. It was his idea, but we collaborated on the paper with some other colleagues, looking at basically the angles of this bone and showing how it increased. And so it got basically bigger and bigger and rounder from really quite a long way back.
So it started off as a crescent carpal.
No, it starts off as kind of a blocky cuboid thing, and then slowly kind of opens up.
I was thinking it'd be like a Jaffa Cake advert, but I'm wrong.
Sadly not. But it was really quite neat that you could track this change getting bigger and bigger and bigger, and we know as it got bigger, allowing greater flexion, the feathers in the hand were getting longer. So we think that there's a link. So as the feathers get longer, you need more flexion to be able to...
You don't want them to get dusty.
Yeah, to keep them off the ground and get them out the way. So that's a really key feature that links everything together.
And I love the idea that velociraptors, if you haven't listened to our Velociraptor episodes, go back and listen to that if you can, because we talk about mantling, and that made me very excited as to what these feathers were being used for. It's not just air brakes, they might have been used to kill things, or to help kill things.
Yeah, we should do an episode at some point about feather function, because although we've talked about stuff like mantling and insulation and, of course, flight, you can do lots of other things with feathers as well, and birds almost certainly were.
Can you?
Yes.
You could write very elegant letters.
Yes, I'm not sure that was the primary selective pressure.
Oh. They had to attract bait somehow. Maybe it was romantic letters. You can't prove it, though. You probably can. Shut up.
Let's move on. So another big one is the sternum. So the chest. And you see these great big sternal plates. So again, Velociraptor is a great example of this. They have this pair of huge square bones right square in the middle of the chest, which would be big anchor sites for muscles.
Okay, the thing is, now I'm thinking of Xena Warrior Princess, and this is probably wrong. But square.
Yes. and more in the midline.
Okay, less booby and
less
more.
I was about to say less boobalicious, but you've gone there already.
See, booby we can get away with, because technically, if there are any kids listening, we're talking about blue-footed boobies, which are a type of bird. We're not. But Xena Warrior Princess, I watched that when I was a kid, therefore we're allowed to talk about breastplates, just sort of, but roughly where the breastbone would be, where the ribs are.
So they're a large part of what will become the keeled sternum in birds, which is then what they're attaching all their flight muscles to. So, but again, this is something that a large part of this evolved well before flight, and therefore we're seeing these kind of ancestral traits, so you can see them fuse together in later birds, and then they'll add the keel.
So they start off as little sort of like, xenas, and they eventually join together and become this sort of like fin down the middle.
Yeah, they're basically a pair of squares or rectangles, one each side, and then they will fuse together.
So what were they? What was the purpose of them before flight and before they need those muscles?
They're still going to be attaching quite a lot of muscles. That will allow them to move the arms particularly inwards, which again, if you're grabbing things or doing stuff like that, it's probably quite useful.
Climbing trees as well, possibly?
Potentially, yeah. So there's lots of discussion about how well or not things like this could potentially climb. I think they probably could climb quite well. They're just not necessarily well adapted for it. So, of course, one of these things that we're often looking for in skeletons, we talk about ecological interpretations, is you're looking for stuff that you can see in other animals. So we talked about digging before and stuff like this. And there's an obvious suite of digging adaptations, and so if you see them in extinct species like alvarezsaurs, there's a good reason to think that they're doing that kind of stuff. You don't tend to see this in the dromaeosaurs. They don't have obvious climbing adaptations, but they do have pretty good gripping hands and feet with pretty sharp claws on them and a pretty strong arms and a pretty good range of motion of their arms and hands.
They've also got, like, a massive tail, most of them, which helps with balance?
Potentially when they're up there, though, of course, the question is getting up there in the first place. And climbing is one of those things where animals which really don't look like they'd be good at climbing are often much better at climbing than you'd think. Like goats.
Oh yeah, goats! God, they're mad.
Yeah, and not just rocks. There's if you just Google goats in Morocco are notorious for getting into trees and really getting into quite high into trees with narrow branches and trunks that you really wouldn't think a goat could get up.
I think there must be a glitch in the operating system with goats because there's no. I mean, why? Why? They're just crazy.
It's one of those ones where the truly direct evidence that you'd want, certain specialised claws, certain specialised gripping structures, certain ratios in the hands and feet and ankle joints are not there. But at the same time, there is enough other stuff that makes them very credible candidates for being decent climbers. Pretty much the same as us, actually. We don't have a lot of the stuff that gorillas and chimps have and other primates do. We're not great going up and down trees, but we're also not bad at it. If you looked at our adaptations, you'd say we're clearly terrestrial animals, and yet we can climb trees okay.
Well, it depends on the tree. It depends how you're feeling.
True.
There are some people who are definitely more adapted than others.
True.
But also, our minds, we just use tools. So, why do that when you could chop the tree down? Boom.
Yes,
anyway.
problem solved. But we've got semilunate carpals, we've got sternal plates.
That's the thing that links them to... And so we've got chest plates and we've got carpals.
There are loads of others, but I don't want to go on forever. So a nice little one that you see are things called uncinate processes. So these are little kind of prongs of bone that come off the ribs. So if you think about the ribs of most animals, they've usually got a kind of Y-shaped head, so kind of two little prongs, and then the long, usually curved bit, which is the main bit of the rib.
Okay.
And what birds have, lots of different birds have, and a bunch of dinosaurs, again, Velociraptor is actually a really good example of this, is they have an extra little prong halfway down the long arm of the rib that points backwards.
Yeah.
And these are basically attachment sites for extra bits of muscle to help move the rib cage, so when you're doing deep breaths, you can expand and contract the rib cage a bit better.
Interesting. So why... I mean, for birds, that kind of makes sense because one assumes they're high... In my head, I'm going, well, they're doing lots of aerobic activity that requires deep breaths and all the rest of it.
Yeah, flight is hard work.
What does this tell us about velociraptors and that they needed this extra rib control?
On the one hand, it might just be generally beneficial. I know that sounds a bit of a lame explanation, but if something is an improvement, natural selection will favour it. If these animals happen to evolve a feature which means that they can pump their lungs a little bit better or a little more efficiently, they don't necessarily have to be super strong runners where being able to be a little bit better like that is going to be a huge advantage. It still is an advantage, even if there's not any huge pressure on them right now. However, I suspect in this case it probably is something like that. If you are running around a lot and doing lots of aerobic activities, or even bordering on anaerobic activities, in other words, you're doing so much stuff you're running short of oxygen, then this would probably be quite a good adaptation. Okay,
I'm gonna nerd up on you now. I'm gonna say that anaerobic activity isn't about running out of oxygen. It's about doing something really quickly before you need to. Because aerobic activity, it's sprinting. You're doing all of that.
It's more complicated than that. Yes.
Yeah. So I'm just saying. I know I know something, we can go. That's far more complicated than that. Yeah, exactly. Because I know so little. Could we turn, because there's a thing, right? And it's not a pterodactyl. It's It's not a no, it's fine, it's fine. It's not a pterodactyl, but it begins with P and it means hollow bones, which I know that they do, like they have, because we've talked about the fact that they have hollow bones because some of them are so very large. You need hollow bones, and this is all the. You know what the word is? It begins with P.
Pneumaticity.
That's the one. I knew it wasn't pterodactyl. We're good.
though pterosaurs are also pneumatic, so that's one of those traits which goes right the way through dinosaurs and probably to the origin of dinosaurs and their nearest relatives, which include things like pterosaurs. So that's probably actually a almost pre-dinosaurian trait, which is then inherited all the way through the dinosaurs and then into birds.
So we have bone marrow from which we make red blood cells. It's proper, nice, strong bones that you can hit with a club and survive. So why do dinosaurs, why do they have this? I mean, birds, it makes sense because you want to be up in the air. Pterosaurs, it makes sense because you want to be light as possible. Why does a velociraptor? Why would it be a beefy velociraptor?
Well, it's fundamentally the same reason. If you can make yourself lighter, then obviously you don't need as much muscle to move you around. You don't need as much food to eat to power that muscle to move you around. These are generally quite good things. The other thing, so bone marrow is an interesting one that ties into 2 or 3 odd little different things simultaneously. So we always talk about birds having hollow bones. But the truth is mammals actually have hollow bones. When you get the bone marrow out of a bone, it's hollow in the middle because the bone marrow is in it. There is a cavity for it. Now, the difference is staggering. That is a relatively small hollow in a very big bone, and the equivalent of a bird will be a massive cavity in a very thin bone. But there is that slight oddity of it's hollow, therefore it's a bird bone, isn't really quite true. It's the question of the extent of that cavity. So that's the first thing. The second thing, so bone marrow, yes, birds mostly and dinosaurs presumably under the same system wouldn't have been producing their red blood cells in their bone marrow because that's where your red blood cells come from. And birds at least have a special organ where they do this separate in the body. But bone marrow is then a weird thing, and this actually, red blood cells are an interesting thing, and this links back to the pneumaticity problem. So our red blood cells are actually really, really efficient. They've got rid of the nucleus, so there's actually more capacity for oxygen carrying per cell.
They're like donutty shaped, so they've got maximum surface area.
Yeah, right. But birds and reptiles don't do that, so their red blood cells still have a nucleus in them. So they're actually not that efficient as oxygen carriers. Where they beat us, though, is that they're more efficient at getting oxygen in and out, in part because they have this air sac system, which extends into the bones and increases. So there's not a lot of air transfer going on the air in most of the air sac system, and certainly not what's going into the bones. But the way they have built their lungs fundamentally actually allows better oxygen transfer. So they're kind of more efficient at getting the oxygen in, but they're less efficient at carrying it around, and the two probably just about average out.
What are their lungs like then? That they're just better lungs?
The main thing that they do is their lungs are actually a circuit. So when we breathe in, the air comes in your mouth and down your trachea, and both of your lungs inflate and blows up, and then both of them deflate. So the air takes the exact same route. It comes all the way down and goes all the way back out. What birds, and we now know a bunch of reptiles, are doing is the air is basically coming in and going into one lung and then across into the other lung and then back out. So imagine it more like a coat hanger. So it comes down the side, it's more like round one, round the other, and then back out.
It's more like a circulatory system with your heart and your blood and everything else is what they're doing with the actual air.
Yeah, it's more complicated than that because they're shunting it between air sacs as well as the lungs in different places.
Does that mean they're breathing in and out at the same time?
No, so they... Yeah. Imagine if rather than kind of amorphous air, think of it as basically a unit of air.
Okay.
So the first unit will come in the mouth and into the first lung. Again, it's more complicated than that. It goes like into an air sac and then into a lung and then another, whatever. We'll just treat it as if they had 2 lungs and nothing else. So into lung 1, from lung 1 to lung... One.
Here, I will deposit my oxygen.
Actually, it's probably doing more both simultaneously. And then from lung 2 back to the base of the trachea and then back out the mouth. So
so it's spending a longer time in their system.
Yeah, and probably encountering more things. We didn't really finish talking about pneumaticity.
Sorry, no.
Pneumaticity is universal in birds, so all birds have it. Varies the degree to how much they have it. There are complicated systems of, say, these air sacs that expand from the lungs, and then they expand both into the body cavity and into the bones. We tend with dinosaurs to only ever really talk about the bones because, of course, the ones which would be in the body cavity, there's really no direct evidence for them.
Yeah.
You can sort of trace them, actually, from which bones get invaded. So some things just have it kind of in the neck, which would make sense because it's kind of an extension of the lungs and the sinuses. But then some get them in the arms and in the dorsal vertebrae. Again, relatively close to the body, relatively close to the lungs. But in more derived things, they go down into the legs, down into the arms. There's a thing called Eriostion, which I can't remember where Eriostion is from now. It's fairly closely related to the allosaurs. And that has things like pneumatic furcula, the wishbone, and things like this. And there's another one, the furcula. So we talked about this on our live video
back in August
for the 20 people who tuned in.
It got more than 20 people live. It's had more views since then.
Has it? Even better. But yeah, so we have clavicles, so the little bones that kind of run from your shoulder to your chest that you can feel just kind of under your...
They're the things that break when you fall off bicycles and things.
Yeah, and then your arm hangs down because your muscles don't hold it up anymore. But in birds, they're fused together into a single bone, which is called a furcula, but
or
you
a wishbone.
colloquially know it as a wishbone. Yep. And then dinosaurs have that too, and they have a furcula. It's a fused one, and Velociraptor, T-Rex, all the way down actually to some Triassic things, and even in other lineages. So the early ancestors of the sauropods, we found a furcula for some of them as well.
Weird.
So again, it's a very common dinosaur trait, which for a long time was supposedly unique for birds, and we now see it all over the dinosaurian tree, and shows that it's been around for 100 million years before birds got going. So yeah, you've got your semilunate carpal, you've got your furcula, you've got your pneumaticity, you've got your uncinate processes.
One thing that I've seen on the Natural History Museum website is they sort of divide the dinosaurs up by their, I think it's their pubis, it's the hip bone sort of thing, a way that the tail and everything else is connected to the body. Explain all this to me, because this basically, it's how you divide up dinosaurs, isn't it?
So we've kind of mentioned this right back at the start, one of the first couple of episodes, and it's related actually to the kind of fundamental divisions within dinosaurs. So we have the ornithischians, which we've mentioned a number of times. So that's your Stegosaurus and Triceratops and the hadrosaurs and ankylosaurs and all kinds of other things are all in a group called the ornithischians, which literally means bird-hipped, because they have a feature which birds have, which is, if you look at their pelvis side on, a pelvis has three major bones. It has the ilium, which runs along the top. It has the pubis, which kind of points forwards, and it has the ischium, which kind of points backwards. And in birds, the pubis unusually points backwards. So rather than pointing forward, it's kind of reversed, and so it has both the pubis and the ischium pointing backwards. And so the ornithischians are named for that because they have a backward-pointing pubis. Now, they actually sort of don't. What they have is this weird... Yeah, I know, it's one of these things that, like, that's an issue, because except for the bit that doesn't. So what they actually more have is a kind of Y-shaped pubis, where one bit points forward and one bit points back.
Okay.
And then, of course, birds are not ornithischian dinosaurs. Birds evolved from a group called the Saurissians, which have the normal condition of a forward-facing pubis.
This is wrong. Okay, so hang on. The thing which identifies the old dinosaurs as being like birds aren't the dinosaurs that turn into birds.
Yes. In the defence of the people who came up with this, it was a really good idea 150 years ago when we didn't know that birds evolved from Saurissian dinosaurs. And it was intended effectively as an aid memoir, not as a direct comparison, but as a, here's kind of what they look like so it's easy to remember, because everyone knew that birds had a weird pelvis.
So what sort of pelvis did theropods like T-Rex have?
All the sauropods and all the sauropodomorphs and most of the theropods have a classic Saurissian pelvis with a big forward-facing pubis. But once you start getting into the ones that are closest to birds, that slowly rotates. And you find it pointing forwards and then mostly down and then very down and then slightly back and then mostly back. So we talked
is
about
that like through time as well as across species?
more or less, though, allowing for the enormous gaps in the fossil record and things that we don't have in places that we'd like to have them. But you look at something like the therizinosaurs, which we've mentioned before, and the giant claws, but they're herbivores and they've really pushed the pubis quite a long way down. It's definitely not pointing backwards, but it's also not really pointing forwards either. And you can start to see how that's changing. And again, by the time you get to things like Velociraptor, Microraptor, the Troodontids, and the things that are very, very nearly birds, their pubis points backwards at this point. And so that is a feature that and it's very much a bird-like one, not like the weird kind of slightly Y-shaped ornithischian one. And so, yeah, that is a unique feature.
Can't believe that they would do that to us, though. Why not just change it? Stop calling it ornithischian. That's just annoying.
Yeah, well, that's the thing. We'll just overturn 150 years of nomenclatural...
Just rename it. Just rename it.
Convention.
Or at least change the name in other things so you don't automatically assume. Okay. I want from a structural engineering point of view, what's the difference between these pubises in terms of what they can do and what they can't do?
In the case of at least some of them, so things like therizinosaurs and why we think probably the ornithischians did it, because even though the ornithischians now have this kind of Y-shaped one, what they don't have is a pair of pubes that meet in the middle. So they've kind of opened them up into this open space. Basically because it's opening the chest cavity up. And again, we've talked about this before. If you're a herbivore, you want to do lots of digestion of plants for a good long time, and therefore you want a really nice big gut. And so if you stick your pubes right into the middle of all of that, it does kind of limit the space in your chest cavity. Now, it is a pain for doing certain things in terms of your leg musculature, but on balance, the trade-off is probably in the favour of big gut. Quite why the birds did it when they did it the way they did it, that I don't know, because I do not know enough about their biomechanics.
Maybe they were laying more eggs or something. No, hang on, no, because they would have been the other way around, sorry.
No, they do lay a lot of eggs, relatively, or at least large eggs for their size. So things like therizinosaurs may well be doing the same thing, because remember, those are herbivorous. But dromaeosaurs certainly aren't, and they're very close to birds and have basically a reverse pubis at this point. Yeah, I'm sorry, I just don't know that. I suspect it is known, I just don't know it.
I'm gonna say one word to you, okay? And that word is perching. Are they dinosaurs? Could most dinosaurs perch? Because I know Triceratops technically could rear up a bit like a bird, but they've got a big tail, so maybe not.
Perching classically involves the fact that the first toe, so the first digit on the foot, is reversed and basically points backwards. So that
of course. Yeah.
Some of the toes come round the front and one toe comes round the back. Various birds do weird things. So parrots have done a weird thing. So they have, I think it's parrots are what's called zygodactyly, where they have like two toes pointing forwards and two toes pointing back. And tree creepers, and there's other arboreal birds. There's various weird versions, but your normal bird...
normal birds take their thumb, and it's their thumb that they've got at the back.
Yeah, so their foot will look much more like our hands if you point your thumb really backwards. That's what they're doing. So when they're gripping a branch, the three toes are going round at the front and one's going round at the back. I don't think there are any dinosaurs that we're confident could do that. So Archaeopteryx is one where there has been a fair amount of discussion, and people have looked in the literature and said they think it's doing that. But what it looks like is that actually that first toe probably has more flexion and can move in more directions, but as a result of the fossil then getting basically flattened when it's preserved, that toe has kind of been pushed backwards. Right. So it's more that it's been forced into a position that makes it look like it's pointing backwards rather than it could actually do that. And therefore perching appears to be a more derived characteristic which came along after the origin of powered flight and things were really quite up in the trees a bit.
But we've talked a bit about their posture and how they have that S-curved neck a bit like a bird would. I mean, I'm obviously talking about theropods here. Is that bird-like or is that not bird-like?
Yeah, when you see these fossils, you know, they are often remarkably bird-like in how they look. There's a lovely photo in a big book on Archaeopteryx of a dead pheasant where it had decayed and it was basically just left with the big wing feathers and the big tail feathers. And it's almost identical to the famous Berlin Archaeopteryx specimen, which is on the cover of every single textbook. So that's quite similar. But actually, in terms of kind of like living postures, there's some real similarities. I'm pretty sure we've talked about them brooding on eggs when we did the eggs episode. That is the same. We now have multiple dinosaurs sat on nests of eggs. And if you've seen a hen on a nest or anything like that, it's the same. They've got the feet under the body, and their arms and therefore effectively wings at this point are outstretched and pointed backwards and would have been covering the eggs effectively. It's a pretty characteristic brooding posture, and we see it only in birds and dinosaurs. And even just this resting posture. So we have two dinosaurs. The more famous one is a little thing called May, which means the sleeper or sleeping.
That's M-E-I. Yeah.
M-E-I, yeah. That's a rare one like Tyrannosaurus rex, where it's mostly named by its full name, which is Mei Long, so sleeping dragon. But Mei Long isn't the only one. We've got a couple of others like this as well. And it was preserved in a resting posture. It's often described as sleeping. I stuck in a paper that I don't think that's a particularly good term, because lots of animals will enter these postures when they're not asleep and they're just resting. So I think resting posture is a better term than sleeping posture.
Or dying, as it turns out.
Well, right, but animals that are taking shelter from things. Again, for if you chase chickens around a farmyard, which I did as a kid on my grandparents' farm, one of their kind of defensive postures is they end up kind of squatting down and hiding. Now, they are not asleep. They are very alert and awake, but the posture is actually quite similar. But anyway, we see this. So you see the legs folded up under the body. You see the arms folded up by the sides. And again, thanks to their semilunate carpal, their hands are pointed backwards. And then the head and the neck is tucked under one arm. And if you've ever seen a duck or a goose asleep at the side of a pond or a lake or a canal, that is exactly what they do. They turn around, point the head backwards, and put their beak, or in this case the nose, back under one of the wings. And we have dinosaurs preserved like that.
So we can presume that they didn't sweat very much and therefore didn't have bad BO. Because of... Unless they really like the smell of their own BO, of course.
That's always likely to be a reasonable inference, yes.
Oh, excellent. That's...
They did not have sweaty, smelly armpits. I think we can go with that one quite safely.
Did they have... Because, if you've ever looked at the back of the chicken, right, they've got this little spot with ooze coming out of it, which is their...
They have an oil preening gland, basically,
preening gland,
which produces oil, and they can use it for their feathers.
Do you think dinosaurs had that?
I wouldn't be at all surprised if they did. We don't know, because that's a soft tissue structure. Yeah. And it wouldn't preserve, and there's no... So we talk about soft tissue structures that you can't see. We also talk about kind of a thing called osteological correlates. So in other words, things that turn up in the bones that we know correlate with soft tissue structures. For example, actually, pneumatic bones. We can't see the air sac, but the fact that there's a hole in the side of the bone opening up into the bone where there's a big cavity in a very thin wall is a characteristic of this. This is one that's not going to have an osteological correlate, annoyingly.
They could have had like saliva or something adapted as well, couldn't they? Things
will groom in lots of different ways. There's been some tentative suggestions that some of the feathered dinosaurs had teeth that were adapted for grooming. That might sound a bit silly, but there are actually mammals that have something very similar. So a famous one is the Dimopterans. So they're called colugos, or better known as flying lemurs, but they're not lemurs. So these are they're a giant...
I hate zoologists. I really do. You guys.
But this is actually why taxonomy is so important, and why you should stick to formal taxonomic names, because when you say things like flying lemur or things like raptor, it can mean totally different things to different people. The Dimopterans are a weird lineage of mammal which consist only of Dimopterans. They're not rodents, they're not squirrels, they're not lemurs, they're Dimopterans. But anyway, these big things, some of them are really quite big, from Southeast Asia. They're big gliders. They open their arms up with big membranes between all the things, and they glide around. And what a lot of them have is these little comb-shaped teeth. Literally, I've got a cast of a Dimopteran skull at the office, and it has a whole bunch of little grooves in the incisors at the front of the mouth, just like a comb. And we think that there's some evidence that they're basically using them like a little brush, because obviously their fur is really important at keeping their membranes clean and make sure they don't have parasites and stuff. And so they've specialised some of their teeth to help them groom.
Like a cat's tongue, but more permanent.
Yeah, but there are some fairly buck-toothed dinosaurs, and there are some with some odd kind of serrations on the teeth that don't quite match what we'd expect them to. And it is possible that they are doing something similar. You know, grooming is important to birds. Grooming is important to mammals. It is going to be important for big animals completely covered in feathers. I mean, there's one interesting question is quite how did they do it? I mean, we've got things like Utyrannus. It's a tyrannosaur. It probably weighed a ton plus. Maybe getting on for 2 tons for a big one. How is that grooming places like the back of its neck? You know, its feet aren't going to reach, its arms aren't going to reach, its head's not going to be able to reach.
Well, I mean, isn't it like any other bird? But just because it's scaled up doesn't mean.
But birds have really flexible necks and usually long beaks, and tyrannosaurs really don't.
Okay. Does this imply that either they were bald in that spots that they couldn't reach, a bit like, you know, the way the vultures just keep themselves clean by not having feathers there, or they were much more pack animals than we, you know, much more social than we think they were?
Well, there's a bunch of possibilities. Well, first of all, vultures are mostly bald because of heat loss rather than keeping clean.
I thought it's keeping clean.
That's often said. It's almost certainly not true. So could they have been bald there? In some, yes. In the case of Utyrannus, we have fossils that show it had feathers all across its body, so that's definitely not the case. They could have been doing mutual grooming with other animals. They could have been doing things like scratching on trees. They could have used effectively cleaner birds in the same way that we have...
Pine-scented Utyrannus. That'd be nice.
Yes, that's a little dangle for your rear view mirror. I'll get the museum to start selling them. But they might just do other things. You know, there's things like the Sumatran rhino, which few people have heard of, is really kind of furry. It's not like the other rhinos. And, of course, they cannot reach the back of their neck to have a good brush or anything like that. What do? They mollow in mud. They wallow in mud and do things like that. So you don't necessarily have to be able to reach every bit of you. You can roll in the mud, you can scratch yourself on trees and rocks. There are other ways round it, but the central point is you're right, you know, grooming is going to have been important for these animals, and it would be very interesting to know quite how they're doing it and what the implications are for bits that actually they can't clean properly.
Another thing, though, I think we should bring up again, though, because we mentioned it when we were talking about the reproduction episode, and also identifying the sexes of the dinosaurs, is the medullary bone?
Medullary, sorry. I've only ever heard it as medullary. That doesn't mean that someone else doesn't call it medullary. It's one of those Diplodocus, Diplodocus things. Medullary may be correct, but I haven't heard it.
But this is because lady dinosaurs and lady birds do the same thing. When they need to produce eggs, they store extra calcium in their thighs.
Well, ladybirds are something else. They're little red and black insects that fly around and eat aphids.
Yeah, nice. I see what you did there. Clever, isn't it? Anyway, but
Sorry,
dinosaurs. But this is a thing that birds and dinosaurs both do. Is they store calcium.
Yeah, and so do some other reptiles as well. In fact, I think most reptiles do, but that at least does tie things together. And again, as we talked about in another episode this series, you know, the elevated thermal physiology and the growth rates are showing that dinosaurs have, you know, many, potentially nearly all dinosaurs have a relatively elevated metabolism that is more bird-like. And again, if you look at just living animals, the only things that have that kind of metabolism are birds and mammals. Birds are clearly not derived from mammals, though that was an idea that hung around for a very long time. I was reading papers on that when I started my undergraduate degree. It was a dying hypothesis, but there were still a couple of people going, no, they've got all these physiological traits in common. Somewhere birds ultimately evolved from mammals. It was called the homotheria, so the hot, basically literally the hot animal hypothesis.
Okay, so when were there birds then? Were there birds? I mean, because I know there's this idea that, you know, the asteroid hit and then the dinosaurs all died out and then there were birds, but presumably the birds must have been around before the asteroid hit.
Yeah, for the thick end of 100 million years.
Okay, quite a while then. Quite a while.
Yeah, so there's this kind of myth that because the birds survived and the extinction of the dinosaurs, in some way the kind of dinosaurs turned into birds as a result or through that process. No, they'd been around for, about 100 million years at this point. So it's one of those odd little contrasts. So the transition from non-bird to bird through dinosaurs, through all these different lineages and the evolution of all these different traits and their changes and their progressive evolution and increase or development, is one of the best documented transitions in biology. If you want to know how you fundamentally change one lineage into something really very different, in this case, birds that fly, the dinosaur bird transition is one of the best that we have. It is spectacularly well studied and with a phenomenal amount of fossils that deal with it. The exact origins of them are really uncertain, though, because we've got a huge gap right where we'd want it. So the middle Jurassic.
Okay, that's really early.
Well, Archaeopteryx is somewhere in the mid to late Jurassic.
Whoa.
So we've already got Archaeopteryx even then. So most of these spectacular feathered dinosaurs that have come out of China are from the early Cretaceous. So these are lineages which their ancestors appeared before birds, but those individual species have come.
So Archaeopteryx was before T-Rex. That's weird in my head.
Yeah, by a huge margin, by like 75 million years. Yeah.
You might not know this, but I want to ask it. Do you know, have we got a bird fossil? I know we got Bellur, don't we? Because we're talking about whether Bellur is a bird or not. But do we have any actual, like sparrows? I don't know, ducks? Are there anything that we found?
So there is an alleged possible duck type animal in the Cretaceous.
Oh, wow.
It's probably not a duck in the sense that you are thinking of a duck. But basically, no, but right. So because you've got to remember how we describe groups and define groups. So there are basically three big splits into birds. There's the Paleognaths, which is ostriches and kiwis and rheas and some other stuff. There is the passerines, which is almost all birds, and the other group is the Gallo-anseriforms, which is the game birds and waterfowl, and that is ducks, geese, turkeys, pheasants, chickens, and all this stuff. There is a putative duck relative, which is a Gallo-anseriform, so it's definitely from that group. So we know that group has evolved and split off before the extinction of the dinosaurs. And I believe the analysis suggested that it is on the duck side rather than on the chicken side. But of course, that's not the same as it's a duck.
Fair enough. So, potential duck in the late Cretaceous. That's quackers.
At a real push, yes. Oh, very good.
Well, let's go and speak to someone who's actually worked a little bit on research. I think she's worked on Archaeopteryx before, but we know her best as the punk biologist. It is Lucy Eckersley, so here she is on her Archaeopteryx investigating ways. What's your relationship with dinosaurs? Do you like dinosaurs? Did you ever?
I like dinosaurs. I think they're fantastic. I actually also did my undergrad dissertation on Archaeopteryx, but that was many years ago, so don't ask me to quote anything.
And what did you?
No, you're an expert.
What did you do on Archaeopteryx?
So I was looking at the kind of Archaeopteryx and the features that Archaeopteryx had in terms of bird-like features and dinosaur-like features. So things like whether it could extend its arms, wings, past its vertebral axis, so it could take off from a standing start like a pigeon does when you stamp it, and which it couldn't apparently, and so it could only glide.
No, not surprised.
Yeah, and then it still had vertebrae in its tail, which birds don't have. It still had teeth, but there were many things. It was it had quite large pectoralis muscles, which birds have obviously to power flight. Although you're going to tell me now it doesn't.
I don't know, but it doesn't have much, if anything, of a sternal plate, to my knowledge. So it's running off large muscles but a small sternum, which is a
exactly,
weird
yeah. And there was a discussion about.
So it's like beefed up.
Yeah,
it's chunky.
It didn't have the skeletal. It didn't have the keel, the sticky out bit that all of that muscle attaches to. It just had a pretty decent sized muscle, and it didn't have the correct ligament that runs through that area that allows for that flapping flight. So my kind of conclusion was that it probably lived in an area, again, from what we know, with lots of trees and lots of larger pterosaurs, and one of the mechanisms that it used to get away from those animals was it would glide, and it would do phugoid gliding, so it would just glide away from them rather than like flapping powered flight. So that is essentially all of my knowledge of dinosaurs.
Oh, it's a good dissertation.
Yeah.
That's pretty good. It's more than I knew.
It was pretty fun. But yeah, since then, I've mostly been working on animals that I can, like, grab and touch now, like fluffy ones
aren't
and
made
stuff.
of rock.
So exactly, yeah. I have got to say, I had enough of the, like, very flat animals. I wanted, like, a 3D animal at that point.
Archaeopteryx does suffer excessively from flatness. It's a real problem. Is that it's been run over
Every time, always in that position.
How many Archaeopteryx specimens are there? Because I know there's the famous one, which is what, 1920s, or is it even earlier? It's 1890s.
Oh no, much earlier.
Darwin time.
Yeah, 1850. So
wow.
Darwin, not too long after The Origin of Species was published, we have Darwin writing a letter to one of his colleagues saying how pleased he is that Archaeopteryx has been found, because one of the things he'd been criticised for is he argued that there were these transitional forms, we just hadn't found them yet. And then, lo and behold, a long-tailed, toothy bird with feathers turns up, which pretty much nail on the head for what he was arguing for. So definitely around that time. There are about a dozen specimens, mostly fairly complete, as in most of a skeleton, but there's some that's a head. There's one called the chicken wing, because it's basically just an arm. But Archaeopteryx has had quite a lot of revisions to its taxonomy recently, and what was one genus and one species is now 3, if not 4 genera, I think.
Lucy's getting very excited by this.
This is
yeah, so it's changed repeatedly. So what a few years ago was Archaeopteryx and there was only 12 specimens, and everyone knew the 12 specimens, and now it's much more complicated.
This is very exciting, but also I think that's one of the things that, like, makes you feel older, is when stuff that you studied in your degree is now not true at all.
Yeah, it's not what you thought it was. Yeah, and yeah.
Do you have a question that you want Dave to answer? You'd like Dave to answer? It doesn't have to be about Archaeopteryx. It could be about anything.
Well, dinosaurs would be good.
Yes.
I've got a question about dinosaurs, and it's kind of bringing in a bit of what I do. So I do a lot of wildlife photography, and because of lockdown, I do a lot of bird photography, because that's what's around me at the minute. And so birds are extant dinosaurs, and they're what we have now that you have evolved from dinosaurs. And so many of them have such incredible sexual dimorphism. You know, you can see that in birds that you see just in your garden. Absolute differences between the male and female of the species. And so I was wondering what we knew about sexual dimorphism in dinosaurs, and if we could pin down any particular traits or ornaments that any species had.
Oh boy. So
Just, like a really easy little question.
This is something I know loads about, and I've written about a dozen papers on this over the last 7 or 8 years.
Buckle up, everyone.
So, the really short version is that evidence for sexual dimorphism in dinosaurs is almost non-existent. It's been claimed multiple times for loads and loads and loads of different species, and there's a whole bunch of apocrypha out there which really need to die horribly. A big one being that Tyrannosaurus females were bigger than males. That's like a thing. And that really commonly, that comes around again and again and again and again and again. And there is no evidence for it whatsoever. It was suggested once, because actually in birds of prey, it's very common that females are bigger than males. But these have all kinds of weird ecological drivers associated with them, and hunting and nest defense and stuff, which really wouldn't affect tyrannosaurs. So there's no reason to think predatory dinosaurs would be under the same selective pressure of birds of prey. Therefore, there's no reason to think that females would be bigger than males. The idea that actually you can spot that there is a bigger and a smaller Tyrannosaurus, which one would rather would be male or female, again, has been suggested multiple times. The data doesn't stack up. And I've written a couple of papers on this stuff, specifically with a friend of mine called Jordan Malland, who's works for the Canadian Museum of Nature in Ottawa. And what we were looking at is actually this problem is, can you even tell this in dinosaurs? Because in dinosaurs, you've got a couple of big problems that you don't have in other things, or in living things. So first of all, our data set's really quite limited. Like, we've got loads and loads and loads of T-Rex fossils, but most of them are bits. The number of decent animals that we've got where you can make a reasonable estimate of how big that animal was is a couple of dozen at most, and probably less than that. So it's not like we've got hundreds and hundreds of individuals. We've got 20, maybe 30 at a real push. That's not a lot to work from. The second problem that we have is the way that these animals grow. If you look at mammals and if you look at birds, what they tend to do is they grow very, very fast to get to their adult size, and then they really slow down. And they might grow a bit more, but they basically hit adult size and stop. So if you take an animal that lives a long time, we're a great example. I mean, we're a bit unusual, of course, but even if you take, big birds like ostriches, like albatross, like hornbills that might live for 20 years, they're basically full size within 2 or 3 years. So for a 20-year lifespan, 90% of that time, they're one size, and that's adult size. Whereas dinosaurs aren't doing that. They might grow quick, but it takes them years and years and years to get to full size. And so that means if you sample a random selection of the population, most of the time you're not getting adults at full size. Or at least, even if you are getting them more often than not, they're still only a relatively small percentage of your data set compared to if you did it for mammals.
How do you know then if you're looking at an adult dinosaur? Would it be like growth plates that have been fossilised?
That's a
growth plates. What's a growth plate? Honestly.
So now we're getting into more subdivisions. So, growth plates are mostly a mammalian thing, though they do turn up in some other stuff, including pterosaurs, weirdly, but not dinosaurs or crocodiles. And that's when long bones are growing. There's basically a little gap at each end. So you have the main bit of the bone, and then a little gap at each end, and then the end bit of the bone. And those gaps is basically where all the growth is going on, or at least a huge amount of the growth to make them longer.
So that's why your knees hurt more than like the middle of your legs when you get growing pains?
Possibly.
Sure.
I don't know. I mean, I don't know. But anyway,
me and Issy are both 6 foot, so we do remember the growing
Dave's
pains.
massive as well. Dave's proper size. We're all human size here. Don't worry.
But yeah, no, dinosaurs don't have growth plates, annoyingly, but they do have, or at least not in limbs, but things like their vertebrae, so the backbone, as with all vertebrates, basically, it comes in 2 chunks, and those chunks fuse together when they're getting close to adult size, when they're finishing growing. So that's one way we can tell them, for example. Another one is things like their ornamentation features, things like frills on ceratopsians. They start small, and when those animals get close to adult size, they tend to inflate and become very big very quickly. So if they've got all the kind of bells and whistles, they're probably adult size. If they've got fused vertebrae, they're probably adult. If they're very big, if you've got lots of them, and these are all the big ones, those are probably the adult ones. So yeah, there are ways of telling adults from juveniles. So going back to our sexual dimorphism, and of that data set, we probably don't have that many animals that are proper full adult size and may themselves even keep growing. And even if most of them are adult, again, if it was mammals, it would be 90+%, and it's dinosaurs and it's only 50 or 60%. That still really constricts your data set. And between those two factors, it means pulling out differences between males and females is extremely difficult. If you imagine that on average, males are 20% bigger than females, that's a pretty big discrepancy. There's some really good studies on reptile sexual dimorphism, and 20% bigger in linear terms for males and females puts you at the upper end. There are not too many species where there's that kind of difference. But when you're only dealing with a data set of what might be a dozen or 24 animals that are at adult size, that's not enough to get any kind of statistical signal to pull them apart into 2. I mean, as Izzy was just saying, all 3 of us are about the same height, but you 2 are well above average height for women, and I'm a smidge over average height for men. So if we were the sample size, you can see why everything goes to hell. And the really short version of this is, particularly when you're talking about this kind of sexual dimorphism in terms of overall size, if you keep growing, a female that's, say, 4 or 5 years older than a male will be about the same size because she's got 5 years growth. And so it is going to be incredibly hard to tell older females from younger males. If you're a bird and you just grow to adult size and sit there, then if you did a big sample, you'd find lots of them that are big and lots of them that are a bit smaller, and you go, okay, and not much overlap in between the 2. It's fairly easy to say that there's 2 there. Even if you're not sure which is the male and which is the female, you would find 2 clusters. Whereas now we've got this horrible smear because those younger males are the same size as older females through almost the entire growth series until you get to the very upper end. That ruins it.
Yeah. I can feel your pain a little bit as well with like the small data set. So in doing my masters at the RVC, I worked with Scottish wildcats, and there are like 30 Scottish wildcats now ish. Unfortunately, they are massively critically endangered for lots of different reasons. But yeah, there's an extremely poor data set, and also there are so many biases in terms of like their behavior and whether they're hybrids, in terms of how they behave and how likely it is that we will find that. I was looking at RTAs, so ones that have been hit by cars, and so how likely they were to be there was a biased number anyway. And I know there's loads of biases within the fossil record, so you just got problem on problem on problem.
Yeah, exactly. So our analysis suggested that you need around about 40 animals of each sex to be able to reliably get a signal, provided they have relatively strong dimorphism of, say, 10 to 20% differences. We basically have almost no dinosaurs where we have, 40 plus 40, 80 specimens. Even if we do, there's no guarantee that that's a roughly even split between male and female, and even then there's no guarantee that their dimorphism is big enough to fit our criteria. In other words, it's basically undoable, at least on the body size front. The second one is, do they have features where the males have it and the females don't? And again, they're almost nothing. We don't, there are no ceratopsians, the horned dinosaurs, Triceratops, Centrosaurus, Pachyrhinosaurus. There are no things where one sex has a big frill and horns and the other doesn't. We have no Stegosaurus or Stegosaurs, which one has plates and spikes and the other doesn't have anything. There are things like the hadrosaurs, the duckbill dinosaurs, where there are some that don't have crests, but as far as we can tell, they are different. They appear at different times and in different places, the ones that do have crests. So it's not a male and female split. There are crested species and crestless species. We just don't have them. There's basically one that might be, there is I think a pretty good example, though incredibly known from actually only 2 specimens. And this is one of the oviraptors or oviraptorosaurs from Mongolia. So the alleged egg eaters that were misnamed, but actually probably ate eggs. So this is a kind of cassowary looking thing that's about 4 or 5 foot high, so shoulder height. Lots and lots of feathers. And we know that from some of the fossils of their near relatives in China, a lot of them have these beautiful tail fans, like a mini peacock fan on the tail. And there's a pair of specimens, literally 2, found side by side, died together in Mongolia, of these oviraptorosaurs, where one has a tail with really quite different articulations to the other that make it look like it's very good for flipping it up and flipping it down and moving it around. And the suggestion is that that is the male animal, and it is good at flipping its tail up and down, because that would give you no real mechanical advantage for running and jumping and moving, because remember, there's lots of tail muscles attached to the legs. But it would be good if you had a little fan on the tail, which we know a bunch of them do, and you want to flap it around and do sexy dances with it. And the animal next to it is otherwise anatomically indistinguishable. It looks basically identical. It's the same species, only it doesn't have this way of flapping its tail around. And even though that's only 2 specimens, I think that's one of the actual probably best cases of sexual dimorphism with a male having a display feature that a female lacks that we have for dinosaurs.
Is there, and I know that probably the answer to this is the fact that in birds, it's much more likely for the male to have the ornamentation or to have the bright colours. Is there any particular reason that you're thinking it's the male that has that in that dinosaur, or is there a possibility it could have been the female?
There is a possibility. So in the vast majority of cases where you see these kinds of differences, where one is bigger than the other, or it has the flashy things that the other one doesn't, it's the male which is the special one, for want of a better phrase.
How dare.
Prettier. It's the male that's pretty.
Yeah.
Showing off more.
The male which is more divergent from the ancestral state. Darwin made this point. You look at pheasants, for example, and all the females look pretty similar, and all the males not only look very, very flash and showy, they all look different to each other, which suggests that all the females are the same as their ancestors, and all the males have evolved into something a bit weird. And mostly this is just an investment thing. Laying eggs or giving birth or lactating if you're a mammal, and things like this cost more energy. And so if you're the female, you are investing heavily in your offspring. And also, females are insured of maternity, whereas males are not insured of paternity. So as a female, it's worth investing in your offspring because at least you know they're yours. And so if females are putting loads of energy into their offspring, they don't necessarily have lots of energy for growing bigger or putting flashy things on or running around and fighting other things or going out and spending lots of effort finding a mate.
I'm feeling like a failed female here. How about you, Lucy?
Yeah, totally failed. Extremely failed female. I've grown really big.
I've grown really big too, and we both like fighting, so this is...
Fighting and brightly coloured hair.
Yeah.
Like, really failing here.
But every so often, either it's mutual and males and females are doing similar amounts of investment, and then males and females look very similar to each other. And I and colleagues have argued that this might be going on with a bunch of dinosaurs, to explain why both sexes apparently have these features. Males are displaying to females and females are displaying to males. And every so often you get a thing called reversed sexual dimorphism, which is where the female is the bigger or showier one and do very male-like things. So the classic example
like
of this
jacana.
is the jacanas, yes, the lily trotters.
Yes.
So these birds with absolutely enormous great feet. They look like coots, but just their feet are twice as big as they should be. And yeah, females still lay eggs, but other than that, it's effectively everything is reversed. The males build the nests, the males sit on the eggs and do all the incubation, they look after the babies and do all the feeding, and the females grow really, really big, and they run around and beat the hell out of each other and fight for the right to get hold of males, and then beat the males up until the males mate with them, and then lay their eggs in the nest and make the males do everything and run away.
That sounds like a
Wow.
perfect life.
They're the bigger, showier animals, and they have completely, effectively flipped this system. And the females are acting like males, and the males who have much higher investment aren't the pretty ones and aren't the big ones and do all the work.
This is getting into it too much now, I know, but there are different...
No, it's not. Keep going.
There are different drivers for kind of sexually selected traits in extant animals. So, you know, the kind of... the different hypotheses for why birds look a certain way, and there's the idea of honest signalling. So the fact that you are healthy enough to be able to have these traits shows that you're a worthy partner. And I mostly just want to say this on a podcast, but could you talk about the sexy son hypothesis and whether dinosaurs have that?
Yeah, so there's these two kind of broad theories for why sexual selection operates, and one is runaway selection and one is sexy son hypothesis. Though sexy daughters also applies in context, but it's become called the sexy son hypothesis, with the idea that things are an honest trait. So I am a healthy animal because I've grown this great big flashy showy tail, which is effort and work, and then I have to spend time looking after it, and I have to drag it around.
And it looks
all the
lovely,
time.
Dave.
And then if any predators... Thank you. Predators are more likely to spot me and more likely to eat me. And so the fact that here I am showing off, going, look at my beautiful sexy tail, means that I must be doing something right. I have grown a big tail, and it is nicely coloured, and nothing has eaten me, and I have groomed it, so I clearly don't have any parasites, and I've got lots of food, and yada, 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 and therefore I'm worth sharing mating responsibilities with, and next generation, and this will kind of grow and grow. So the runaway one is the idea that for whatever reason, females, and of course not necessarily, but usually females are selecting males, females just like that look. For some reason they think that looks nice. And as a result of them liking the look of whatever that is, whichever male happens to look like that will probably have more offspring. And, of course, his sons will inherit the tendency to look like him, and his daughters will inherit his mother's tendency to like that look. And you can see how that can accelerate quite quickly with more and more daughters liking more and more males that look like that, and the whole thing, again, can accelerate. On average, I think the sexy son hypothesis, I think most people think, is what's happening most of the time. But there are at least a couple of examples of runaway sexual selection hypothesis apparently in operation. So one is swordtails. Anyone who's kept tropical fish probably knows mollies and swordtails, these fairly small, pretty little things. And swordtails literally just have a big spike off the bottom of the end of the tail. And mollies and Mollies are a very close relative of swordtails and don't have this. If you take a male molly and just glue a little kind of fake swordtail onto the end of him, female mollies think this is the best thing ever and go nuts for these males. There's no particular obvious advantage for it. There's no particular previous selection for this. They just seem to like it. Or for whatever reason, they are hardwired to think that this is sexy. And you can see, therefore, how, presumably, at some point in the evolutionary history of this lineage, one of the males grew a little spike and the females went, well, hey, and it didn't take long before swordtails were a thing. And as far as we can tell, that's more or less runaway sexual selection an idea in operation. What's causing that, we don't necessarily know. I really haven't read up on it much. My suspicion is that it's probably something to do with just looking different. Lots of animals in the wild have relatively small pools of available partners to reproduce with. Inbreeding, so reproducing with relatively close relatives, is generally not a good idea. At some level, you want them to be fairly close to you because you want your own genes to do well, and if they're a relative of yours, you will have some more of your own genes there, and so that will pass on. On the other hand, if you're too close, any nasty genes that you have are more likely to double up and knacker things. But in general...
Hey, Charles Darwin married his own
exactly,
cousin, so.
right. And it's interesting, actually, if you look at the basic genetics, a straight first cousin is about the first time that the odds shift very heavily from there likely to being problems with any children to there not being any problems. And my understanding is that if you look in most cultures, that is like the big barrier. Anything closer than first cousin is often a huge taboo. First cousins are generally considered frowned upon but okay, and anything beyond that everyone considers fine. And it aligns really quite closely with the odds when you do the basic genetics. But I suspect that side of runaway sexual selection, and at least as we're seeing it in things like mollies and swordtails, is probably linked to something that looks a bit weird and a bit different and a little bit exotic, is probably nice and unrelated, has a very different gene set. That's really good for immunity against all kinds of parasites and diseases. Novelty is really good for resisting parasites and diseases, and that might just inherently be attractive. So it might be less that they're hardwired for that particular little trait, and then that trait happens to pop up, and then everything kicks off, and more that anything that looks a bit different is suddenly really appealing.
So does this mean that, if there was a T-Rex out there who had blue eyes, suddenly they'd have done ever so well, and there'll be lots of T-Rex with blue eyes?
Quite possibly.
Nice.
Interesting.
Yeah. I mean, I honestly think you can make a at least tentative case for that whole thing in humans. We talk about, ooh, exotic, ooh, sexy. I mean, it is a thing that someone who looks quite different from what you're used to experiencing is immediately found attractive by, I think, most populations everywhere.
I really want to let him continue this so he digs himself a little hole somehow. But... yes. No, and who do you find exotic, Dave?
A deeper hole. I've already started digging.
Well, Lucy, does that answer your dinosaur questions as to who Dave finds attractive?
Yeah, it does. I think it's a really difficult area, and I like how you were like, well, there's not much evidence, but I have published loads on it in the past. So
that's really confusing. That it's the secret sexy sun syndrome. It isn't the ones with the sexy sun. Oh my gosh, that's so confusing.
Yeah.
But I like the fact there's two different selection methods happening. That's quite exciting.
Yeah, and there is evidence for both of them. So at the time when these things were kind of came up with, they were competing hypotheses, and the expectation is that probably it was one or the other in just about every case. Certainly, it is harder to find evidence for kind of runaway versus this handicap idea that shows that you're very healthy. But there are at least a couple of examples of it. So it is definitely a thing, and it is not an either or. And therefore, of course, almost inevitably, there's probably somewhere it's some kind of combination of both.
Birds of paradise. They're just weird.
Birds of paradise are
Well, because every week we have a different guest, but you're not that guest. And then I was like, oh, we don't announce the guest until just before, even though they just heard it in the pre-tro. It's very complicated. It really is very complicated. This week, what I thought we should talk about, because we haven't really talked about, we've talked about dinosaurs, we talked a bit about their behaviour and that sort of thing. What we haven't talked about is how we know about dinosaurs, and that is fossils. Now, I'm aware that there are different types of fossils, because there are the types which are bones, that sort of thing, and then there are things like footprints. So,
yes.
Which don't count as fossils or are fossils? I get confused.
They are. So, we basically have two broad classifications of fossils. And the first are body fossils, which are, bones and teeth and shells when it comes to other kind of animals like that. And anything directly attached to that, which is the original animal that has preserved. So occasionally that means things like muscle and scale. Those are all body fossils. And then we have things that we call trace fossils, and those are remnants of where animals were or things that they did. So footprints, nests, eggs, anything like that.
Eggs should be bodies, because eggs are like... I sound very pro-life American.
Pro-egg. Yeah. You get these weird combinations. So, like, if you've got an egg which has an embryo in it, then that's sort of simultaneously a trace fossil and a body fossil. And if you have a bone with a bite mark on it, the bone is clearly a body fossil, but the bite is a trace fossil. So they're not 100% separated. But fundamentally, we talk about body fossils and we talk about traces. And of course, most people are used to thinking about body fossils. They may have considered footprints. But we have these whole groups of different fossils, and all of them are ultimately some kind of record of past life.
But if we talk about body fossils for a moment, because I'm going to admit this, and it makes me sound a little dim. I was a teenager before I realised that it's not that a fossil bone is not the same as just a really old bone. It is actually, it's turned into a rock, isn't it? It's not like when you dig up, like, you know, when you regularly dig up graveyards. What am I admitting to here? You know, if you unearth human remains, that are even 1,000 years old, they're not fossils. They're still just dry bits of bone. And there's a difference between that and what we're finding with dinosaurs.
Pretty much the definition of a fossil is something that has mineralized. So, the reason our bones preserve so well, of course, is they are already very heavy mineralized, but it is a biological mineral.
Is it calcium?
Yes, calcium carbonate is the big one, and there's some other stuff in there too. But that is a living biological tissue, and then when organisms die, that dries out, and obviously bones are pretty robust, and not a lot of things eat them, which is why they survive well. But fossils are where those things have been buried and undergone a chemical and physical reaction under compression and buried deep in the earth and all the rest of it, and they have become mineralized. They have taken on the characteristics of the rock that they are in, which is partly why they're also so many random different colours for dinosaur bones, because of all the different conditions.
I just thought they just did that to paint them, so when they put them on display. I'm an idiot. Okay. So it's literally because they're different types of rock.
Yeah, quite literally. And that's why they'll respond differently. And so some are relatively easy to get out of rock because they are much harder than the rocks that they are in, and some are very hard to get out because they are soft and the rocks are hard. But it's worth stating that you have literally turned the bone into stone, but it is a perfect copy. We talked last week about things like medullary bone. You can cut the bone up and polish it and look at it under a microscope and look at the individual bone cells.
Okay, so it's not just the shape.
No, it's not some crude replica. It is literally the physical thing has turned into another thing. I mean, I guess a vague and imperfect analogy would be toasting a slice of bread. The outside still actually has all the same little bobbles and textures, and the bubbles that you could see are still replicated, and the fundamental thing is still the same, but it's now hard and crispy, whereas it used to be soft.
Okay, I get you. I think
it's an imperfect analogy. It was the best thing I could think of at short notice.
Fair enough. So don't put marmalade on your fossils. That is the takeaway from this episode.
That's the lesson of the day.
Dinosaurs are all over the earth. I mean, presumably there are only... Because it's not like every single dinosaur got turned into a fossil, is it? Why are some fossilised and others not?
Yeah, so our general rule of thumb, which frankly we have no idea how accurate it is that it's about 1,000,000 to 1. So for every million living individuals, one might have become a fossil. Wow. And then, of course, we've actually got to go and find it at the other end. So that further limits our ability and cuts the numbers down. But yeah, quite simply, if you're a random animal wandering around, and you die for whatever reason, there is a very good chance you'll be eaten because you were killed by a predator. But equally, even if you haven't been, and you've been drowned or just die of starvation or you're ill, there is a very good chance that scavengers will get to you, and then bacteria and flies and fungi, and you will break down and dissolve and decay or erode. The sun and wind and rain will get to even the bones and take them apart, in which case no possible preservation. If you get buried because there's a sandstorm, or you're in mud, or you're in a river and then there's lots of silt in the river and you end up on the bend and whatever else.
I love that. You end up on the bend. Geographers listening, he means meander. I know things.
Yes. You can get buried. That stops things getting to you. That stops you decaying and has a chance of you being buried further and further and further and compressed and mineralized, and that's how you get your fossil. But yeah, these events are fundamentally very, very rare, but it's also why under the right conditions, suddenly they become very common. So things like volcanic eruptions tend to kill everything, including things like bacteria, which means you're far, far more likely to be buried than you would if you're just out on the middle of a plain.
I was going to say, the chances of getting buried and not having anything eat you is, I'm trying to think of it, and it'd be really hard to do it, because that does explain, though, why you get certain places being better than other places for fossils.
Right.
If the conditions are right.
Yeah.
So if Lyme Regis in the UK is the one I've been to, and that's pretty good for your little shells and ammonites and things.
It was a bay then, lots of mud, lots of silt. And marine sediments are always good for this, because animals that die sink to the bottom and are out of the reach of many animals already automatically. And then if there's loads of mud stirred around, there's a very good chance you'll be buried. But these patterns means we have some bizarre anomalies. So if you go to a modern rainforest and even a big animal dies, it will break down extremely quickly with the heat and humidity and all the stuff that's going on. So actually, even though modern tropical rainforests have huge numbers of animals, vast diversity of life and huge numbers of life, they're terrible for producing fossils. Deserts have very few species and very few individuals of those species, but decay is almost non-existent because everything just dries out pretty much instantly. So that means actually, if you look at the fossil record, our general knowledge of things like rainforests is awful because things don't fossilize there, and our knowledge of deserts is amazing.
Wow. So we've got a really weird perspective.
Yeah, and of course, at least we know that, so we can work on, we know that those biases are almost certainly in place, but it's weird that we have a really good understanding of desert habitats and desert species, and a very poor understanding and a very poor knowledge of what were probably the most diverse areas.
But you guys seem to dig in areas which are already like deserts. Is that because they were deserts then and still are deserts now, or...?
So some are. So Mongolia and China, I spent a fair bit of time. I asked a senior paleontologist, a guy called Jim Clark at George Washington State, who's a brilliant researcher while I was out there, because Jim had been digging there for decades. I went, Jim, what did this look like 70 million years ago? And he kind of went, like this. It was very dry. There were few plants. In places where there was water, there was a lot of plant material, but those were few and far between. And the environment there was probably not a lot different to what it was now. Other places that's not true at all. But yeah, there's a reason we go to deserts and badlands and places like that, and it's not because they're necessarily good for fossils. There are other places which are equally good or even better for the fossils, but it's the places that we can get to them. To get a good fossil, you want something that's still underground. You want to get it before it's been exposed and is being eroded. If you're in a place where there's deposition, like a floodplain, well, sediment is not going away, sediment is increasing, so you never find anything. So you've got to go to a place where ideally sediments are eroding, otherwise you go back every year and never find anything new because nothing's changed, and where you can get to the ground. And that means places where there's not a lot of plant cover, and of course not a lot of other things like human habitation. And deserts and badlands, therefore, is lots of rock on the surface. Nothing grows there, so there's very little agriculture. No one lives there because there's very little agriculture. And there's lots of erosion happening because there's no plants and soil to protect the rocks.
It's also presumably, there's political reasons and funding issues as well as to why you go to certain areas and not others. But you've been to places like China, so that's pretty cool.
Yeah, so I spent 3 years at the IVPP, so that's the Institute of Vertebrate Paleontology and Paleoanthropology. So I had 3 years there, and as a result of that, I went digging in sites all over China. I didn't get to dig very much. I was there as a postdoctoral researcher, and while I did get to join various excavation teams, that wasn't really what they were paying me for. So they wanted me to spend my time working on stuff rather than digging holes.
I love the way you're sounding like you're making excuses, but to me that is a bonus deal because digging sounds hard. I'm mates with, I know a lot of very cool. No,
I know people.
I know people who are archaeologists. Very cool It's an oxymoron. You can't say it. The cool archaeologist. But the thing is, there are cheats you can do. Because the thing is, I'm thinking that you go off to some sort of site in China and it's this massive plain. And where on earth do you go dig first? Because it's not like there's a little sign that says fossils here. And if you're an archaeologist, we got, you can go into plains, you can do surveys, you can work out a straight line means human habitation because we love walls. Everybody loves a good wall. So, there are ways to get around it. How on earth do you pick where your dig sites are if you are a paleontologist?
In general, knowing where things are. So obviously, the world geologically has been mapped in a fair amount of detail because we're looking for various resources and minerals and we want to know what the soils are like and so on and so forth.
You follow the oil and mineral companies.
Yeah, to a degree, but we have mapped the world geologically at a fairly fine level. So it's not too hard to look at a map and go, okay, we know there's a big fossil bed here where we've dug before and found stuff, and it's covered by this and below this level. And over here, a couple of 100 miles away, is the same layer of rock with the same thing above it and the same thing below it. That's probably a good place to go digging. We should go and have a look. And so you would send a team out to have a look around, just to see, have a look at the rocks, have a look at the stratigraphy and the layers, see what the type of preservation is. Maybe it's different. You got to remember, even paces away from one point to another could be the difference between a riverbed and a floodplain. And so the preservation could be different yards apart, even within a single fossil layer.
There's different layers of rocks with different dinosaurs in each layer of rock, almost because of the preservation. So it's almost like somebody's trodden on a trifle. So the layers have become mixed depending on where you are.
Well,
some bits are sticking up and some bits are lower down. And
I mean, I'm really not a geologist because I came through a zoology background, but yeah, you have not quite necessarily that with mixing things up, though stuff can get flipped over occasionally.
Oh yeah.
But it's more like, an absolutely enormous trifle, and some bits have been dug out, and that's because erosion has removed some of it, and other places have been built up, and the layers weren't laid down evenly in the first place because the sponge fingers or the fruit was patchy. And so, yeah, you've got to kind of reconstruct all these different places to try and layer out and work out where these things correlate with each other.
Yeah. Let's say we get to a site and we know that there's likely to be dinosaurs here because there are layers that correspond in geology things says, and you get there. How do you know where to dig exactly when you get there? I mean, is there like an X-ray gun where you can just go, boop, 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 there's a dinosaur in the rocks over there. Boop, 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 oh, there's a big one over here.
People have tried that stuff. So want to avoid talking about it because it's already this podcast, but you can't avoid it. Jurassic Park, the start of the first film, they're out digging and they got the big machine that goes thump and it does a sonar through the ground and it comes back and they go, oh, that's the fossil. People have tried it. It basically doesn't work. Because the short version is, as we've just discussed, so your bones have absorbed or are fundamentally very similar to the rock that they're in. And of course, what things like sonar are working off is differences. And so if your rock is an almost identical density to your bone, then there's no difference, and therefore there's no signal to pick up.
So how do you find them then? So what do you do?
You walk around.
This is not sexy or exciting, Dave.
It's extremely non-technical. But the thing to do is you walk around. In particular, you walk around valleys. So again, there's lots of erosion going on in these places. So there's all kinds of hills and valleys and stuff. And what you tend to do is you walk in the valleys, because what's usually happening, of course, is that hopefully your bones are at lots of different layers. If they're at one single layer, you would just walk along that layer and just look for anything. But mostly, your layer is either very thick, and they can be hundreds of meters thick, or there's just dinosaurs throughout in various different places. And so what you're actually looking for are little chunks chunks of bone, because a skeleton which has eroded already is falling apart. It's exposed to the sun and wind and rain and plants, and it's going to disintegrate, or it already has disintegrated. What you want is a skeleton that's still underground. And of course, if it's completely underground, you won't find it. So what you really want is a couple of little bones sticking out of a cliff face. Or, of course, if they've eroded a little more than that, they'll fall out of the cliff face and roll down the hill. So as you're walking down valleys, you're constantly scanning all the hillsides in the area and looking for bone that's coming out. And that, of course, takes a real eye, because it's often a very similar colour and a similar texture to the local rocks.
Does anybody actually do that, though? Do you actually see a little bit of bone and go and find a dinosaur?
Yeah, I've done it. And I was extremely proud when I did it. And yeah, it seriously, it was a chunk the size of my little fingernail, maybe even half the size of my little fingernail. Just walked along, saw this dot, that looks like bone, went up a hill, it was bone, dug around it. It's not just a fragment on the surface, there's a bone going in behind it, dug behind that, and there's another bone, dug behind that, and there's another bone. This was a place in Xinjiang in northwest China, and there, when we get fossils, it's a very unusual environment. You almost never find anything. Like, we took a team of 25 people for 3 weeks and found like 3 things. But when you find something, it's almost inevitably a whole skeleton, and often multiple skeletons together.
Wow.
And in this case, it was a juvenile tyrannosaur that we got out.
Really?
Yeah, and a couple of turtle shells as well.
Hang on, for the rest of us, is a turtle shell a type of dinosaur, or is it just a couple of turtle shells that were just there?
It's a couple of turtles, though I'm using turtle in the American sense. They were probably tortoises, so land turtles. I'm used to dealing with American paleontologists where any tortoise, terrapin and turtley thing is a turtle.
Bizarre Americans. Good thing there are no Americans listening.
Yeah.
So you actually found, that's amazing, just from a little dot. Yeah. And you could recognise dinosaur bone. How far away from the dot were you when you saw it first time?
Oh, probably half a yard. Not far.
Dave. That's amazing.
It's a combination of there is a skill to it, because some people spot things that are, even a team of paleontologists have walked past and just go, no, there, you need to get that. There is a skill to it, but there's also a certain amount of just effort. If you put enough people out and walk around and keep looking long enough, you will find stuff.
And also every year it'll change a bit, because more of it will erode, so it's a constant changing.
Yeah, I mean, I'm really hoping to get into the field next year. So obviously we're on lockdown at the moment, pretty much worldwide. There are probably very few paleontologists getting into the field right now anywhere on Earth. And that means we're going to go an entire year with no one doing any exploration or any digging. Now, on the downside, it means we'll probably miss some things. And when we come back next year, stuff we might have found this year now will have been eroded or destroyed. But really, it means we'll have 2 full years of erosion before we go digging next year. And that greatly increases the chances of you finding something really special.
Okay.
So next year, fingers crossed.
Not all bad news, we hope.
Well, it's kind of swings and roundabouts. On the one side you're not looking, on the other side there's a better chance of better exposures.
So you and your tyrannosaur. So you were out. Were you walking alone, or did you have a group of people ready with shovels?
Obviously, prospecting alone is dangerous in the absolute middle of nowhere, so it's a very bad idea. But equally, having 2 experts stood next to each other is equally a waste of time, because you're just looking at the same stuff and
spread your expertise.
Yeah, but I've been out with people, and someone's literally stepped over something and the person behind them spotted it. But on average, it's not a great use. So what you usually do is prospect in pairs, but you just make sure you're in permanent eye line or a shout away, just in case an accident happens. So at that moment, I was completely alone, but there was someone 20-30 meters away, just looking on the other side of the valley.
Okay.
So yeah, no chance of anyone nicking my credit. I found it.
Okay, fair enough. I wasn't suggesting. So, but when you found it, so it was you two together. You obviously didn't excavate the entire thing at once.
Yeah. So again, I did a little bit of digging on, so I'm carrying a bunch of tools with me. I'm doing a little bit of digging, because there is still the chance that it's what I saw was bone, but it's just a fragment and there's nothing behind it, or it's one bone or a couple of bones and nothing else. So yeah, I went digging for probably 5-10 minutes till I realized there was definitely 2 or 3 bones there.
What bones were they? Could you tell?
I'm pretty sure it was the foot. I'm pretty sure they were foot bones now.
Your toes poking out.
7-8 years ago. Oh no, probably long, more like 9. So did that much, and then immediately, ran to the top of the nearest hill so I could find the nearest 2 or 3 people around, yell, wave over. Because as I say, this is an area where mostly we don't find very much. So I'm not interrupting everyone else's work. Dragged them over. What do you think? Yeah, we think it's that. Cool. Right, let's get digging. So then 3-4 of us spent probably the rest of the afternoon clearing that away. So there was about 15, 18 of us on that dig. But of course, we're all scattered everywhere. And so, of course, pretty much everyone goes back for lunch and goes back in the evening. You don't want to just be chasing people all day. You never get anything done. Expose as much as you could. Realise we're now 6, 7, 8 bones at this point. You've definitely got a good chunk of a skeleton here. Went back to camp with some, of course, now with photos, it makes it so much easier. You can just take a couple of photos and get a GPS, and then walk back to camp and just show your camera. Here, found this. Oh, great. And then the next day, probably half the team, 7, 8 of us, with a pneumatic drill, with a portable generator, portable in the loosest. It takes 4 people to carry the damn thing. Basically an engine block in a little housing.
You can see why they don't digs halfway up mountains.
People do, and there is stuff excavated from mountains, but it just gets so much harder. As every time you factor in all these differences. In this case, we could drive a Range Rover to within about 100 yards of it, and so even carrying this damn generator and the pneumatic drill up and down the hill, it's not too bad when you've only got to go 100 yards. But yeah, then obviously we just start going into the hillside and just clearing the hill out, because obviously we now got to go in. And then when you start getting down to the bones, you excavate around it. So you're very careful because you don't want to smash anything up. And then that's when you cover it in plaster of Paris, like every single film and documentary, and indeed like they were doing in the 1870s. I think that kind of technique was developed.
And so that's to stop the bones from crumbling up?
Yeah, it's just to protect them. You're going to stick them in the back of a car and drive them a very, very long way, and they're probably going to go in the back of a train or another one at some point, and at least some of this is going to be cross-country. Then they might sit in a lab for a couple of years before you get to them.
Years, wow.
Yeah, so just having something which protects everything and makes it safe and means that if you drop it, you don't ruin everything is a really good idea.
So do you wrap each bone? I mean, it must take ages if you've got to wrap each bone individually.
It varies. So I found, probably my second greatest find was a little foot of an alvarsaur. We talked about alvarsaurs last time, the tiny little anteaters. And this foot is the size of my thumb. And it's like all the little foot bones and all the little toe bones and the claws all together just sat. And it was an unusual preservation. This is from Inner Mongolia, so north-central China. And basically it was just a foot with very little sand on it at all.
Like a lucky rabbit's foot.
Yeah, almost a complete piece. And so I literally found it, picked it up, wrapped it in a bunch of toilet paper, put it in a cloth bag, and that was the limit of work that ever was required to that fossil.
Toilet paper, Dave. You're not being romantic and adventurous with toilet paper.
Yeah. So everyone carries reams of toilet paper in the field. First of all, for the obvious necessity when you're miles from anywhere. And secondly, because exactly this, it's really nice and soft and flexible and it's light to carry. And you can wrap stuff in awkward shapes with it and pad them effectively. So, yeah, everyone carries rolls of toilet paper everywhere, and sooner or later, every paleontologist will face the dilemma of, I've only got so much toilet paper, and this fossil is valuable, but I know I'm going to need some more paper soon. And how much do you commit to the fossil or other activities?
The paleontologist's waiver. That is.
Yeah.
Anyway, so you excavate your dinosaur and it gets put in the back. I mean, I can imagine something, quite small being able to be transported, but if it's a massive, because some of these dinosaurs, they're huge. How on earth do you get the bones out then?
Yeah, I mean, if it's a big skeleton, or if it's several skeletons together, I've excavated that before, a group of several on top of each other, and you don't want to break them up or lose that information of how were they orientated and which one was lying there and all the rest of it. Then yeah, you ultimately left with the choice of either you take out a huge block or you've got to break things. And that's the options. And taking out a huge block isn't always easy. So yeah, I took out a huge lump in China. It was several ankylosaurs, so the armored dinosaurs. We had, I think, 5 of them together, which is actually not that uncommon. You tend to get these clusters of juveniles. And yeah, we took out something like the size of a dining table. It was like, 6 feet long and 3 foot wide and 2 foot high block of sandstone.
Weighed
an absolute ton. We actually had to cut it in half in the end and basically go down the middle and veer around the bones and try not to break anything. But even then, the way we got it out is happily we were not that far from the nearest small town, and so we rented a bulldozer and literally just drove the bulldozer out into the desert. And this it had been plastered up, but just picked it up and put it on the back of a flatbed truck and then drove it to the train station and put it on a train.
I can imagine a lot of people's hearts were racing when that thing picked it up.
But with other stuff, you don't have that option. So one thing you often see in documentaries, and this is particularly common in the US, is, again, Jurassic Park reference, where the whole skeleton is exposed on a hillside and there's paleontologists working all over it and opening up all the bones. Now, that obviously is normally a terrible idea because you want to be doing it in a lab under climate control and with glue to hand and air conditioning and... You know, if someone drops a bloody hammer, they're going to break something. And of course, if it's on a table in a secure lab, that's not going to happen, etc. But a huge amount of the US stuff, even though, of course, it's licensed and permitted, you're on public land where it is very often so protected that you're not allowed to take wheeled vehicles.
Oh, no.
Which means you have two choices, either carrying out by hand or getting a helicopter to take it out. And whichever of those two options you end up using, weight is unbelievably critical. So although they're doing what could be considered a very suboptimal thing in terms of, removing a lot of the protection that you'd actually really like to keep, again, if that's the only way you're ever going to get it out, then that rock has got to go. And so they'll prepare it very heavily and far more than we would ever need to in China, where those rules don't apply.
Is that why, American paleontologists just look so strong and dashing? Do we think that's why? Must be that.
Well, you end up carrying stuff no matter where you go, and digging a big hole in a hillside is a fair amount of effort. On the subject of really big things, again, in the past that wasn't always easy either because people just didn't necessarily have the transport or the places were just awkward. There's a famous location in Tanzania called Tendaguru, which in the 1930s was German East Africa, and the Germans were doing some major excavations there, and they were pulling out what we now call Giraffa titan, which was called at the time Brachiosaurus. And the big bones of those animals are 2 meters long and when mineralized are, 200-300 kilos. And they had footpaths were the only things, through the mountains, or at least through very rugged terrain to get them to the coast. And so they were carried by hand. And that meant that any large bone basically had to be deliberately, if it wasn't already, because often a lot of them are broken, deliberately broken into carryable chunks.
Oh, no.
And they would, a femur that size would be broken into 4 or 5 pieces and then strapped with ropes onto a bamboo pole so that 2 or 3 people could physically just walk it, 20-30 miles out of the site to where they could get it onto a horse and cart or to a motor vehicle.
I've been watching Better Call Saul on Netflix, and there's an episode where he has to walk through the desert for a bit and carrying stuff, and oh my goodness, no spoilers here, don't worry, but just the thought of it, that's a lot of work. Okay, so you got your bones back to, but they're going to a museum, I assume.
Generally, yes.
Yes, I'm just bored. Yeah, I don't know if there's like a special, well, first we have to take them to the Dinosaur Center emergency room and make sure that they're not alive. I don't know. So you take them to the museum, and what happens to them then? Yeah,
so I mean, a lot of stuff goes into storage because. So again, productive places, so things like Inner Mongolia or in China, we can find more stuff in 6 weeks than their preparation team can clear out in a year.
Wow.
So you tend to actually accumulate stuff. And in these plaster jackets, they are safe for decades, even potentially centuries. And, fossil. I once wrote a somewhat joking blog post saying that all research money in the world should go into paleontology. Right, but anything we don't find and excavate and put into a museum and protect will erode and be destroyed and gone forever. Yes, obviously we want to save things like elephants, but elephants can breed and produce more elephants. Fundamental chemical structures of things will be the same if we run the Large Hadron Collider in 200 years or if we run it tomorrow. That fossil will be gone and will never exist exist again if we don't collect it. But that means that, therefore, our policy is even if there's stuff that we know we're not going to prepare or we may not get to for decades, if we don't collect it now, it's gone, and it's probably worth having, so we better get it. And so, yeah, all museums tend to have a big backlog of stuff they really like to get round to, but haven't yet because they've always found something more exciting in the interim. Yeah, and there are warehouses often of unprepared material. I mean, it's not like Raiders of the Lost Ark, of a warehouse that goes on forever, but, a very large building or a separate part of their storage facility will have literally tons of material.
It's going to be very strange for future archaeologists. They're going to be like, what on earth happened here? There are all of these dinosaurs and humans living together.
Yeah.
I mean, because they're not all put on display, are they? Either they're just
yes, like any museum, the really good stuff is on display because that's what people want to see, and it's easiest to communicate what it is about and what it shows and what it means and how we know that. But there's tons and tons and tons and tons behind the scenes which aren't on display, and often that rotates through for special exhibits or goes on loan, but, a huge amount of that is usually the scientific collection.
I have a question about how you extract the fossils from the stone. Do you do what they said? Do you still do what they said they did, like when I was a kid, which is use dentist drills? Were they just making that up?
No, that's pretty much what we use.
Really?
Yeah.
Doesn't that take ages though? Because they're tiny dentist drills.
Yeah, they can. Well, so we have some bigger ones with nubs the size of pencils, but ultimately they're doing the same job, which is that you want to be able to dig into something very, very hard, and of course in the case of tooth enamel it's extremely hard, but you also want some real precision and delicacy. And so these are the tools we use. They're basically, in the case of the dentist and us, they're basically tiny pneumatic drills. It's a barrel with a needle point at the end, and that point is either going in and out or usually just vibrating on the spot. And then with a hose out the back, which will go off to a big air compressor somewhere. And you have bigger ones for, bigger stuff, and some even super fine ones if you're working on very delicate stuff.
When you're working on delicate stuff, do you picture yourself in the dentist's chair? Does it make you jump?
No, that's
okay.
I don't have to do that. Fortunately, it doesn't. That hasn't got into my head yet. But thank you for placing that idea there.
Oh, you're very welcome. You're very welcome. Next time you're at the dentist's, just think of dinosaur fossils.
but that is basically what we're doing. And again, huge variation. Fossils that are prepared on super thin slabs. Where you can just crack it and it pops out. You often don't have to do very much. Sometimes the rock is very hard and the bone is very soft, which makes life very difficult. But if you're working with something like sandstone or most mudstones and siltstones, which of course are very common because that's exactly the kind of stuff that bury things.
Sediments.
Usually the bone is a lot stronger than the rock that it's in, which is a good start. But the very fact that you've got a bone in, another structure actually gives it a natural plane of weakness. So obviously, while you do need to be careful and you don't want to break your delicate fossils, in general, if you hit it, what actually happens is the rock will crack off around the bone, and you're just trying to do that process in a very controlled and careful way.
Okay, so you're not actually going around whacking them, is what you're saying. You definitely don't do that.
Yeah, so, I mean...
Because what I'm picturing now is, occasionally on these cooking shows, you get people, I'm going to salt bake my beetroot, and they put the beetroot in the oven with a salt baked crust, and then at the end of it they take it out and they whack it, and all of the clay comes off and they're left with the cooked beetroot.
I mean, it's not a million miles from that. I mean, there are videos you'll see online of what we call concretions, where basically balls of rock form around fossils, and if you just hit it with a hammer, they generally crack and expose the fossil perfectly, and that's precisely because it's that plane of weakness. So that is where the rock is going to break and just open it up and show you the fossil. And yeah, for big things, I mean, we need to be careful, but there is a trade-off. You cannot prepare something the size of a sauropod with a drill with a point that's as fine as a propelling pencil. So of course what we do is, if I've got a big bone, the skeleton's roughly articulated, so I've got no reason to think that there's any bit of tail vertebrae or a spare tooth lying next to this bone. I can see where my bone starts. I'm currently sitting, 15, 20 centimetres from that. It's not that I don't need to be careful, but I'm not sitting there with a tiny thing. That's when I can physically get out a real chisel and a hammer, and I can knock off some huge chunks of rock a safe distance away from the bone very quickly and clear out a load of rubble.
Like a cheating Michelangelo.
Yeah, and a finer chisel as I get a bit closer, and a finer chisel as I get a bit closer, and then when I'm down to the last centimetre or two, that's when I'll break out the dental tools.
You have to have a good idea of what it is you've got as well, I suppose.
Right, and so that, and again, so that's where these things vary enormously. So an articulated skeleton, so it's in its natural position, the fingers connected to the hand connected to the elbow, etc. Actually, that sounds slightly wrong, but you know what I mean. But you know what's coming next in the series. I've prepared 5 fingers. This is a 5-fingered dinosaur. There really shouldn't be a 6th one. I can go pretty quickly along here, and the odds are I won't hit anything, and that's fairly safe. I've got a complicated joint, but I know I'm at the back of the skull, and I know that the next bit is probably going to be bulging out, so I'm going to be super careful because I'm expecting a lump here. So yeah, knowing what you've got makes a huge difference.
Just jumping back a bit, because earlier you said that, you've come across dinosaurs where you've got multiple fossils all in the same place together and have all been... So how has that happened? Have they all just been poisoned or something? Why would they be like that?
Yeah, there's a whole bunch of reasons for that. So a common one, is that it was a group of dinosaurs trapped and killed together. We've got a number of different ones where they've got stuck in mud, and you can tell that from...
How can you...
Well, because, if that thing preserved in one go, then, we talked about footprints. All that churning is still visible. So you can see that although there's 7 or 8 skeletons here, all the stuff around their legs is all horribly mixed up. And it's all settled out, and that showed that it was very wet at the time that it happened. And so
they literally got stuck.
Yeah. So we have some like that. There are a couple of examples where we think they literally did get poisoned.
Really?
You can get toxic pools and toxic water if you get these weird algal blooms, or if an animal dies of some horrible septicemia, a predator comes along and eats that. The toxins might be enough to kill it within minutes, and then, of course, a predator will come along and try and eat that.
Oh, wow. So, you got a predator poisoning your predator, and they all sort of, eat each other in a chain of death.
Yeah, and they're called predator traps, and perhaps the most famous one is La Brea tar pits in Los Angeles, where, normally, for a normal ecosystem, big predators are pretty rare and big herbivores are pretty common. At La Brea, they've pulled out literally hundreds of dire wolves and dozens of saber-toothed tigers for a handful of deer and antelope. And hundreds of birds, and particular things like vultures and condors, and that's because of exactly this situation. Something like a deer gets trapped. It's in the tar. It can't get out. It's either dead and smelly, or it's alive and making lots of distressed noises. And of course, every predator under the sun will go free meal, wander over, walk into the tar, get stuck, dies, free meal, predator walks over, gets stuck, free meal, and you end up with literally hundreds of carnivores buried in tar. But we have dinosaur ones like that too. So Wusai 1, so where I found my Tyrannosaur, the reason that we suspected that there was probably a whole skeleton there before we'd even started digging is it's famous for having very few fossils, but when you find them, there's a load of them together.
Okay.
And the interpretation of this is some superb work done by a guy called Dave Ebeth, or led by Dave Ebeth, who's in Alberta, is that basically you can imagine a very muddy, lakeshore or similar, and big dinosaurs, so big 30, 40-ton sauropods are walking through here. And again, we see the mud has been churned up in columns, and those columns kind of alternate.
Oh my God, they're footprints.
Which is exactly what you'd expect from, effectively footprints that have, gone down. The weight of the animal has squidged all the mud out and then sucked it back up as it steps out, and then all the water churns, and you basically get this kind of weird liquefaction of the mud. And so, of course, wherever that happens, it's now super sticky and very easy to get stuck in. And so you can imagine a small animal walking along, or a small group of animals walking along together, wade out into this. It doesn't look different to everything else, and suddenly they're stuck. And then, of course, distress calls, or die, other things come along, they get stuck, and so on and so forth. And so out in Wusai 1, you often find very, very little, because, of course, it was very unusual for these things to form and animals to get stuck in them. But when you do,
there's loads.
Finding 4, 5, 6, 7 dinosaurs and other things like local crocodiles and turtles and other stuff, all in one just vertical column.
Has anybody actually gone in and sort of like
pretty normal,
like done a sort of core sample of this column? So you just get an entire column out.
So these were discovered before I started working out there, but my understanding is, this is basically what happened. Is they found a couple of skeletons together, obviously absolutely ecstatic. Started digging them out, and as you start to lift them off, there's another one underneath.
Oh, wow.
And then you go down to that one, and there's another one under that one. And then at this point, you start to become very suspicious that you've basically found nothing for weeks, and then 5 on top of each other.
It's like the parcel of dinosaurs. This is amazing. With a sweetie every layer.
Yeah, and in the end, they dug out this block that was something like 2 meters high, which of course is not the way you normally excavate fossils.
No. Oh, that's great.
To get the depth to capture everything. And then of course that also meant you could see all the different layers and what had gone on.
Oh, I wish we could display something like that in a museum. I mean, let's talk about museums, because presumably once you've done all the preparation, and if it's a new species, presumably you've described the dinosaur and said, well, it was very large, but technically.
That's, something I really want to talk about in the future is like, how do we name them? Why do we know that they're different species, and how do we differentiate between species and all that stuff?
We'll run out of episode time. This is the thing.
No, I said another time, but we must cover that.
Not all fossils go into the museum, so how do they? And because not all dinosaur fossils are complete, so how do they decide what goes into a museum and what doesn't?
Yeah, well, in terms of display, again, it sort of depends what you're doing. So places like the Royal Tyrrell Museum in Alberta, which is absolutely phenomenal, that's partly built where it is because of the huge collection of local dinosaurs, and therefore, over half their exhibition space of the entire museum is devoted to local Alberta dinosaurs, which is fully understandable. In the UK, we don't have so many, so perhaps it's not a big surprise that there's not tons of.
We've got a copy of Dippy.
But we haven't filled it with British dinosaurs, and then again, not even originals. Like, every single museum worth its salt wants a T-Rex, and ideally wants a real one, but there's only so many to go round. So yeah, a lot of stuff is casts, so replicas. And people say, oh, well, it's a fake. It's not a fake. You've made a mould and taken a copy, so it is an exact replica. It's just not obviously the true original bone. But even very good and mostly complete skeletons, they're never totally complete. Some ribs are missing, the tip of the tail is missing, a couple of bones of the hand are missing. And so those need to be replaced to make the thing look complete. And those are either cast from others of the same species, if possible.
Who are the same size as well, presumably.
Yeah, we have got lots of T-Rexes, so we can get some extra ribs from another one and make copies of them and slot them in. Or you can physically sculpt them if they're very simple bones.
The best job ever.
Yeah, you can make copies from your own thing. If it's missing a couple of teeth, well, copy the tooth in front and stick it in the socket behind. Occasionally they get lumped together. So this was, again, much more common in the past, where people were much more interested in these as display items rather than as for scientific, they were done for the greater glory, basically. There's this giant mounted Giraffatitan in the Humboldt Museum in Berlin, which is absolutely stunning. And it's 4 or 5 animals welded together because they never found a complete skeleton.
Please tell me they called it Frankenstein.
No, but they had enough to be able to make it. So although there's some casts and sculpts and bits in there, like the neck is from one animal, and then the front leg is from one animal, the back leg is from another animal, and the tail's from 2 other ones. And so 3/4 of it is original bone, but it's also not one individual.
I've got to see this thing because I've never seen. Because I know them as Brachiosaurus. So what are they called now?
Giraffatitan, so the Titanic giraffe. It's an absolute horrible name, but
wow, I don't know, Giraffatitan. I'm not too bothered by that. But I have to, because it's one of my bugbears with a lot of these dinosaurs is you don't really, you're not really, like we were talking with Triceratops, and most people, I included, think they were the size of rhinos, and they weren't. They were much bigger. So yeah, I mean, if you could put on a display in a museum, what would you put on? If you had an unlimited budget and you could say, look, you're in your exhibition spaces for 3 weeks, go. What'd you build?
You'd be hard pushed not to include a Tyrannosaurus, because even though for anyone who loves dinosaurs, they're a horrible cliche and ultimately passe. A, I work on Tyrannosaurs, and so I kind of want one. And B, it is, if you want one thing that people will come to see, and if you're running an exhibition and you want to teach them about things, getting them through the door is the first step of that, then you probably want to include one. But yeah, even though I do very little on sauropods in general, the big sauropods, and again, like we say, Diplodocus, which many people have seen, and not just in the UK, because there's copies of them all over Europe and in Japan and in
Russia,
US and other places too. Diplodocus is distinctly medium-sized at best. It doesn't come close to being a big sauropod, and so one of the absolute titans is what you really want.
Yeah. I also want to make a request that you have it so that there's like a trench around it so that people can't touch it, but they're on the same level, because all of the scaffolding usually raises all the dinosaurs up and you don't really get that effect of how big, because we just don't get that scale thing.
Yeah, it's really annoying. So I have this, I have this theory, which is then one of those horribly colloquial things which annoy scientists. I have this idea that people are often very bad judges of the sizes of large things, in part because they have no frame of reference. So I've worked at London Zoo as a zookeeper for a while, and it's only when you physically stand next to, and by which I mean like 6 inches from, a giraffe or a rhino or something, that you discover just how ludicrously big they are. They don't look it, and I think it's because normally, the member of the public, the animal is somewhere within its enclosure, and you are somewhere behind a fence or a moat or both. There's no car, and there's no telephone pole or street light, or something that the exact size of that you're intimately familiar with, right next to it. And museums have that same problem. You might only be a couple of meters away from a T-Rex skeleton, but 2 meters away, when you don't know how big it is, and then as you say, it's raised off the ground, actually really distorts how large it is. And again, the head will then be 4 meters off the ground, and and then you're looking up underneath it. It really warps people's perceptions of these things.
So how would you display it then?
So Fukui in Japan have done one thing which solves it. So they've got several T-Rex skeletons on display.
Show-offs.
Yeah, I know. And as a result, one of them they have basically in its own little side room, and it's just got this giant, square spiral staircase. So there's just kind of ramp that just slowly goes up all the way around it in a spiral. So, of course, if you stand even a yard away from the T-Rex, you can barely see it because there's all this metal gantry in the way. But that's not the point. The point is that you can walk all the way around it. You can even get on top of it and look down on it. And at no point are you more than pretty much an arm's length away from this skeleton. And indeed, actually, this is a cast. But in terms of the perspective, you can get head height. You can be eye to eye with the skull from a meter away. Then you appreciate that, oh my God, I could probably barely get my arms around this thing, end to end. Which you cannot do when you're standing on the floor and it's up in the air well above you.
See, I've got in my head now that would be amazing to have that, to have the skeleton one like you've got, and then next to that,